All right. Uh, Hopefully, we are becoming live. Let's see who can join us. Let's see who can join us. Here. Who? Please join me. Let's see who's here. So Amber is here. Hi. Oh, Sinus is live. Hi. Uh. Let's see if Sinus can join. Let me give you the link. The link. I'm about to take a shit. You got the wrong time. How much time do you need for a shite? You have 15 minutes. Go. All right. So I have a new Big Bang Theory ether-based. Listen. All right, let's think about the ether-based Big Bang, because I never thought about the Big Bang. I never gave it a thought. What happened during the Big Bang? But let me just make sure the audio is fine. I never checked the audio. Wow. Oh my God, the audio quality is so high. Absolutely. Listen to this. It's just, I mean, audio quality is so high. You're hearing me, so obviously the audio quality is completely out of this world. I mean, it's completely worth it to invest in this headset. It's not an expensive headset by any means. This is like how much was it? Maybe like $40 with the delivery, because delivery is not free. It's like another $10 for delivery, so it's amazing quality. Let's see. Where are we? Yeah, let's whiteboard. Let's think about the Big Bang. How can the Big Bang work? Yeah, I've actually multiple new theories. Rope. Oh, Jensen was here. This is the rope wave mechanics. I don't think there's anything interesting in this slide. Okay, so why do we have? I created this rope wave mechanics. What was here? So there was nothing here ever. Rope wave mechanics. I don't remember it. Let's rename it. This is going to be Big Bang. What just happened? Big Bang. This is ether-based Big Bang. So how did the Big Bang happen, assuming ether? So it's not so simple. It's not so straightforward. I never gave it a thought. Oh, we'll take more than that, lol. All right, take I guess half an hour. Oh my god. But are you listening? Anyway, so what was the Big Bang? How did everything start? Well, we know there was a Big Bang. Let's see. No, I can turn it on though. Well, one is the Big Bang, but the other, what was the other? The other was here. Was this. Listen to this.
Hello, everyone. Welcome to the May 2022 Ask Me
No,
Anything
not
edition of Lionsgate
this.
Podcast. I'm your
This.
host, Sean Carroll. Things have
Shut up.
and one of the reasons why I don't know, could it have been some other way? Is it telling us something deep? I don't know. And one of the reasons why I don't know is because just being a field theory, I don't think is right. I don't think.
So he doesn't think that. Let me just check what Cenas is writing. I can't really focus on this today, though. No problem. Finish up and join me whenever. Let's continue listening to. This is Professor Son Kellol. Very, very nice person. Very nice person. He needs hair. He always needs a haircut. I don't know. His shirts are odd. At least he always, almost always, I think he always has a collared shirt, but a bit weird mostly. Always needs a haircut. He's very old, but has black hair. Really strange. I mean, he's old. He is probably 60. This is a 60-year-old. Oh, maybe it's an old picture. No, no, I saw him lately. He looks the same. Anyway, let's listen. Let's listen. Very, very important. So he thinks that the quantum field theory cannot be the ultimate theory. It cannot be the theory of everything. It cannot be the unified field theory. It cannot be that the universe is based on the quantum field theory. Let's hear it. Roll back again a little bit. It's interesting that he says that the world cannot be a field theory. I mean, the correct way to express it is I don't think a field theory is the ultimate explanation. A theory is an explanation. So I don't he should have said I don't think that a quantum field explanation is and it can be an explanation for this universe, for the ultimate substrate of this universe. What ultimately is this universe? It cannot be the quantum field explanation. Oh, I didn't share this tab. Wonderful. Just wonderful. Let's start over. No, what's going on? I can't roll.
I don't know. And one of the reasons could it have featured
So let's listen to the question.
a certain kind of symmetry called local gauge symmetry. So kind of feature force and space. And I think that my credence for answering questions like this is less now than it was 10 years ago. because I've been thinking about quantum gravity in the meantime, and it
One
was
second, let me figure this out. This is 4340. Can I go back?
impact of the smaller incremental steps along the way, but they're important. They're important for the whole story. Joelle Curtis says, "Do you think the
Okay, so it starts here at 4315. Let me make a note of this. Oh, 45, 43. I made a note. 4315. Let's modify it. Let's make another note here. 4315. Let's try and write it down a little bit.
fact that our most successful for the whole story, smaller?" Joelle Curtis says, "Do you
4313 maybe, or 12 even. Joelle Curtis?
think?" But they're important. They're important for the whole story. Joelle Curtis says, "Do you think
Joelle Curtis. Joelle Curtis.
the fact that our most successful theories explain interactions and forces in terms of local gauge symmetries is explanatory in
I don't know what local gauge symmetries are.
any deep sense? Does it tell us something very important about nature or our relationship to it?" Well,
Maybe I don't know. Maybe I'm assuming it's the quantum field theory. It's yeah.
I have no idea. That's a very good question.
So what was actually the question?
In any deep sense. Does it tell us steps along the way? But they're important. They're important for the whole story. Joelle Curtis says, "Do you think the fact that our most successful theories explain interactions and forces in terms of local gauge symmetries is explanatory in any deep sense? Does it tell us something very important about nature or our relationship to it?"
So he's basically asking, let's say, about quantum field theory. Is that the ultimate? I mean, when he's asking, does it tell us anything? Is that the ultimate explanation of reality?
Well, I have no idea. That's a very good question.
That's amazing. He says he has no idea. So it could be that it's like very high level.
I honestly don't know, and I think that my credence for answering questions like this is less now than it was 10 years ago.
Amazing. So 10 years ago, he would have given an answer that maybe it is the ultimate explanation of reality.
Because I've been thinking about quantum gravity in the mean.
Quantum gravity. Why is quantum gravity? I mean, they don't have an explanation for quantum gravity. I don't. Why? Why is quantum gravity driving everyone insane? I don't understand it.
Time, and gravity changes everything a little bit. So for folks who are not experts in these buzzwords, our best current theories of the world in terms of predicting things and being accurately mapped to data and so forth are quantum field theories. So quantum mechanical theories of fields that pervade space. And in particular, they have different kinds of fields, and the forces that we think of, electromagnetism, the weak nuclear force, the strong nuclear force, and gravity for that matter, are all a certain kind of field defined by a certain kind of symmetry called local gauge symmetries. Okay, we won't go into what that means, but there's a certain symmetry property that helps explain the features of the forces of nature.
Yeah, I mean, they all behave basically the same, and all the particles slash waves are interchangeable, and they all interact with the Higgs. They all have some sort of charge, some sort of color, some sort of spin. So there is asymmetry. I guess that's what he's hinting at.
Did it have to be that way? Could it have been some other way? Is it telling us something deep? I don't know. And one of the reasons why I don't know is because just being a field theory, I don't think is right.
And this is now the most amazing statement he's going to make.
I don't think the world is a field theory.
That's amazing. So the world is not ultimately or cannot be a field, a quantum field.
And the reason why is because in field theory, there's an infinite number of things going on.
Because his field has no, it's not real. There are no particles, there's no substrate, there's no medium for the field. His field is pure math. And because of that, it has no elementary size. It's infinitesimal. It's mathematically infinitesimal.
in any one region of space. And
Let's
to
hear
me,
let's hear it again.
field theory. And the reason why is because in field theory, there's an infinite number of things going on in any one region of space.
So in any region of space, it doesn't matter how small it is, you can fit an infinite number of things because his field, his quantum field is pure math. So anything can fit into any size. There's no limit. It's incredible that he doesn't talk about the Planck limit.
Space. And to me, infinite number of things going on in any one region of space. And to me, that means that there could, in principle, be an infinite amount of entropy in any region of space, right? Because entropy counts the number of things that could be going on in a region given its macroscopic features. And so if field theory were right, then I claim that you could imagine state.
It's his claim. This is like a whole paper what he's pronouncing here. And I want to write a paper about it.
And so if field theory were right, then I claim that you could imagine states in the universe where there's arbitrarily large amounts of entropy in any region. But we know that's not true, or we think that's not true, because if you keep putting things in a region of space, the energy keeps going up, and eventually you collapse into a black hole. And black holes have entropy, but that entropy is not infinite. It's a finite number. So that tells us there's only a finite number of things that can happen in any one region of space. And
That's incredible. Because a black hole can form in any region, so you fill any region, any arbitrary region, you fill it up with things, and as you fill it up with things, you're increasing the mass until it collapses into a black hole. And a black hole, he says, has a finite entropy, finite entropy. Finite entropy? So it's not mass?
space, the energy keeps going up, and eventually you collapse
Oh, the energy. So the entropy goes up, so the energy goes up?
macroscopic features. And so if field theory were right, then I claim that you could imagine states in the universe where there's arbitrarily large amounts of entropy in any region.
Entropy just means like you can confuse things. You can mix up things more and more and more. I don't know. I'm rethinking what he's saying, and I'm not sure he's saying what I thought he was saying. Okay, well let's finish and then we'll analyze it more.
But we know that's not true, or we think that's not true, because if you keep putting things in a region of space,
Keep putting things in a region of space. Okay, but is that entropy?
the energy keeps going up, and
Sure, the mass goes up, the energy goes up.
eventually you collapse into a black hole.
Okay, that's for sure, yeah.
And black holes have entropy, but that entropy is not infinite. It's a finite number. So that tells us there's only a finite number of things that can happen in any one region of space. And
Okay.
that tells us that nature is not described by a quantum field theory.
Okay. What did I write as a conclusion? I said there can only be a finite number of things that can happen in any region of space. Sounds like an argument for the particles of the ancient ether. Hmm.
Now we're still
He is basically quantifying uh, or quantizing space itself, which is an argument for the ether. He's saying that space itself must be quantized, if not for any other reason than this reason that it must be. And now you can plug in his argument. You cannot put an infinite number of little things in any finite or infinitely small region of space. Like he's saying, according to quantum field theory, there's no minimal space in which you can put an infinite number of things. In any infinitesimal region of space, you can put an infinite number of things. And then he says that cannot be because ultimately it will become a black hole before long. Any infinitesimal region of space will become a black hole, and that must have a finite entropy. I'm trying to imagine what he's imagining, and I'm having a bit of a hard time.
working on understanding the implications of that, because certainly the local gauge theories that we use are really super duper successful. But once gravity becomes important, it seems that they can't be fundamental, even though they're very successful. How that all fits together, I don't know. So it's
I'm not sure. Actually, on second thought, I thought that I understand, I can imagine what he's saying, but now, because he's using this argument of entropy, and I'm not sure what, I cannot imagine entropy. I cannot imagine. So basically, what he's saying is, according to quantum field theory, you can take any infinitesimal region of space, any arbitrary region of space, and dump in the entire universe into that region of space. You should be able to do that. But he says, but that's not possible because long before that, it should become a black hole. Okay. Yeah, but black hole stretches, sort of stretches space. Space is stretched because inside a black hole, space is stretched. So you should be able to fit. I mean, this is basically a black. He's like having a black hole paradox. The problem, but the problem is that you can't have both. I mean, the the actual substrate of the universe cannot become a black hole. It is whatever it is. It cannot whatever it is. It is. You cannot change it. Making it into a black hole shouldn't impact it. A black hole is an artifact of the quantum field. This is even I'm having a hard time imagining this paradox now. So you're creating a black hole, but a black hole, it stretches. The problem is that it stretches space. Effectively, space is stretched. Anyway, I don't know. I don't know. This is very difficult to imagine, so I honestly don't know.
it's very, very possible that the success of gauge theories in our low energy accessible world is not an accident, does reflect something really deep going on at a profound level. But it's also possible that in some sense it's an accident. In some sense, it's an epiphenomenal, something that would be true in some approximation, but is not very deep or fundamental. I honestly just don't know. It's worth thinking about. Lester Sue says,
Anyway, that was very deep for me. There's a quantum heretic. Let's see, who's this quantum heretic?
May help explain.
I always forget to share. Oh my god. Yeah, I'm waiting for it to start. Oh, I didn't.
I think it's reasonable to question whether we should be quantizing space-time like we've quantized all the gauge theories. If it was classical, then it has a number of intriguing features like the measurement postulate is not needed. That may help explain dark matter and dark energy. Some has a number of intriguing features like the measurement postulate is not needed. That may help explain dark matter and dark energy. Some
He has an explanation for dark matter?
Ideas are so radical, they border on heresy. Professor Jonathan Oppenheim, a distinguished theoretical physicist at University College London, has proposed a theory that may just fit that bill. His provocative framework suggests that gravity itself can remain classical in a quantum universe, an idea that's riling up colleagues and undoing decades of theoretical physics gospel, which asserts that gravity must be quantized. Oppenheim directly refutes Feynman's arguments about the double-slit experiment, while showing how this controversial approach could solve long-standing mysteries, not only with gravity, but also with the measurement problem and the nature of dark energy and dark matter. Okay, Professor, welcome. Take it away.
Great. So I'm going to be talking about the attempt to reconcile quantum mechanics and gravity or space-time, and this is joint work with a number of my students, and Isaac Layton, Mohammed Sajid, Barbara Soda, Andre Rousseau, Zach Davies, and Akutka, etc. So it's a joint project. We can start by asking just a more simpler fundamental question, which is we have these two frameworks in physics. One is quantum mechanics, and the other one is classical mechanics. And we can just ask the question: are these two frameworks compatible? Can we combine them in a consistent mathematical way? So quantum mechanics, we're used to the Heisenberg equation. We have a density matrix sigma, and it evolves.
The Heisenberg or the Schrodinger?
As the commutator with the Hamiltonian, and classical mechanics.
I think he means the Schrodinger.
Has a very similar form if we think of a probability distribution rho. So the probability density rho evolves with a Poisson bracket with the Hamiltonian. So those two frameworks have a very similar form. And we can now ask a very, I think, natural question, which is, can we have a classical system which interacts with a quantum system? So here we have a phase space, Q and P. So we have a particle which lives in phase space. And then we could have a quantum system like a two-level spin-and-a-half particle. And we can ask, can we combine these two systems together in a consistent way?
Oh, sorry. Can you just go back? Because I want to make sure that you're seeing what I'm seeing. Can you go back? Okay, so I'm going to screenshot to you what I'm seeing, or I'll describe it, but I can also screenshot it. So what I'm seeing is it's a Q and P. There's a blue box, and then there's nothing inside the left-hand side, but then there's an equal sign, and then a psi with a dot.
Yeah, there's just,
is that not what you see?
Oh, yeah, I see that. So that's just my bad graphics. So the equal sign is a two-level system. So there's the
All right, so if any of you are confused as well, so this looks like it's saying nothing equals the wave function and the up here for some reason.
There is, okay, this little dot here is a point particle, is the free particle, and then we have the state of the quantum system, which is meant to be a two-level system. And as you can see, I do my own graphics. I don't have a graphics.
Wonderful.
Let's keep going.
Well, this one's far superior.
This is far superior. So this one I also did myself.
Oh, great.
So it's just meant to demonstrate that we all the time we combine classical systems and quantum systems. So for example, in the double slit experiment, we treat the walls of the box and the slits, we treat those classically, and the particles quantum. And in
That's a good point. Everyone treats the box classically and the particle as a wave particle. Yeah.
This, a potential here. The potential we treat classically, and the quantum system is quantum. And that's the case where we have a classical system which acts upon a quantum system. So that we can deal with pretty easily, and we're used to such systems. What we are not used to, we're not able to do, or haven't been able to do until recently, is deal with the back reaction. In other words, we have a quantum system which back reacts on the classical system. And I'm motivated to study this for a number of reasons. One is that these sorts of situations occur all the time where we have a quantum system that we want to treat classically, but it's interacting with another quantum system. But I'm mostly interested in this because I mentioned gravity, and we know that gravity is famously inconsistent with quantum mechanics. I either want to think of a reconciliation where I treat space-time as classical and maybe modify quantum mechanics a little bit, or I may be also interested in situations where I just treat space-time classically. So an example is in a black hole, then the black hole is evaporating, so the evaporation is emitting these photons, which we treat quantumly, but the back reaction is on a classical space-time. Another example is inflation in the cosmology. We treat the expanding universe classically, but the vacuum fluctuations we want to treat quantumly. So it's often the case that we want to treat one system quantumly and the other system classically. But I'm also interested in the possibility that maybe we should not be quantizing space-time. And so I want to go over the reasons why gravity is somehow different to the other forces which we want to quantize, and therefore why we might question whether we should be trying to quantize gravity.
Okay, I just have a quick question here.
Good.
So when I was speaking with Sean Carroll, he mentioned to me that the holographic principle is quantum gravity. And I asked him, how does that constitute quantum gravity? And he said, well, it integrates quantum mechanics with general relativity. He said it's into some unified theoretical construct. I said, well, to me, the way that I understand quantum gravity is that you quantize the gravitational field. So that either is you do some canonical quantization of Einstein's field equations, or you employ a path integral over the metrics. What is it specifically that you mean when you say quantize gravity?
Right. So Einstein's theory of gravity is that space-time bends when a massive object bends space-time. And so to quantize gravity has generally meant that the space-time itself, the metric, so the gravitational degrees of freedom, which is how much it bends, that should be quantized. That's traditionally what people mean. Now, ADS-CFT kind of claims to resolve this in some situations by through duality. And so people would claim that in certain space-times ADS, that the boundary theory, which is a quantum theory, is it's a fully quantum theory. And by definition, you can say, I'm going to define that to be quantum gravity. And then if you have a mapping from the boundary to
I have no idea what he's saying. I'm trying to understand if there's anything that he's saying that I can, latch onto.
what's happening inside in the bulk, then you would, I think, be able to claim that you quantize gravity. Now, the issue with ADS-CFT is that we don't really know if the dictionary is consistent. So there's all kinds of rules that people are still trying to develop, and we don't really.
My gravity, I think, is quantized because my gravity is the ether, which is quantized. I mean, I go beyond quantizing. My ether particles are probably much, much smaller than the elementary particles. And my ether is made out of actual particles, not there's no wave duality. And these particles annihilate. I think that's the Higgs mechanism. Something like that. So my ether annihilates when it interacts and gives inertia to elementary particles. And so I don't have a problem quantizing gravity. Gravity for me easily works on an electron or a quark.
Really know if these rules hold or are consistent. Some people have a lot of confidence in it. My sense of it is that these rules are still being developed, and we still don't really know, if they hold. So, for example, you need to have a whole bunch of things need to, in my view, hold in order for certain paradoxes in ADCFT to be resolved, and we just don't know if that's the case. But I would agree that if
ADCFT, AD what? ADCFT, ADCFT, string theory, ADS-CFT. ADS-CFT correspondence, duality between theories of gravity on anti-de Sitter space and conformal field theories. In theoretical physics, the anti-de Sitter conformal field theory correspondence, frequently abbreviated as ADS-CFT, is a conjectured relationship between two kinds of physical theories. On one side are anti-de Sitter space. I don't know what they're talking about. I haven't looked enough into this.
conjecture holds, and that is a quantization to have a whole bunch of things need to, in my view, hold in order for certain paradoxes in ADS-CFT to be resolved, and we just don't know if that's the case. But I would agree that if ADS-CFT, if that conjecture holds, then that is a quantization of gravity in a certain space.
Though in that case, it still sounds like you have a classical background spacetime. How's that quantizing? Are there other issues?
So, in ADS-CFT, it's a very strange thing that we require this background spacetime and then claim that there's no background, that we kind of don't need it in the bulk and it's somehow emergent. And that may be, that may be successful in the end, but it's a little bit strange in my view that you need to rely on a background classical spacetime in order to get an emergent spacetime. I guess what I find interesting about, say, an attempt to quantize gravity is that if you think about what we're trying to do, so you can see in the slide, you start off with, say, some initial data on a Cauchy surface. So you start off with a space-like hypersurface, and you define your initial your fields to live on that surface. And
I don't know. I don't know what he's talking about. So this is a waste of time for me right now. So this has been a waste of time, but what else did I think about? So what Sean Carroll said, I don't know. Anyway, let's get back to my theory of the Big Bang and the initial inflation, how it could have been. So today I went to I met a friend, an old friend, and he has this chick that comes around, and she's pretty. She's young and pretty, and I told him that I'm interested in her. She's like she behaves like his daughter. So I just told him I'm interested, and he said, "Let me ask her what's going on." Anyway, I never heard back, and today I saw them, and I take a look at her, and I told her, "Wow, you're beautiful." And I think it turned her on like crazy that I told her, let me drive you home. She wouldn't, but as they were driving away, she waved at me and he told me, you have a chance. However, I currently am dating someone and I don't like cheating, so I don't know what to do. I'm conflicted, very conflicted. Okay. Nevertheless, let's talk about the Big Bang. How could the Big Bang have happened? Hmm. How could it have happened? So it's like in the beginning, well, we know, well, let's talk about what we do know. So we know currently that the universe is expanding. We know all the galaxies are flying away from each other. That's pretty clear. We know there is dark energy. We know that there is a redshift, which means that between any two galaxies, here's one galaxy on one side of the universe, here's another galaxy on the other side of the universe. So we know that, let's say that's us. The left one is going to be us. When we look at the other guys, the other galaxy, it it's redshifted. Now this redshift means this color. Well, we know what an average galaxy should look like, I guess. Instead, it's a little bit reddish or a lot reddish. And this suggests the only explanation for this, why should it be reddish? Uh, so why is it reddish? So one explanation is that it's zooming away from us. And as it is zooming away, the light gets stretched. That's one explanation. However, another explanation is that the space, the entire space between us and that galaxy, that space is expanding. Something is filling up, something is being injected into this space, stretching this space and causing the original, let's say, original blue wave, it's stretching it out so it becomes red because it's being stretched. Okay, but why can't it be that this galaxy is simply zooming away? Why can't you say that it's zooming away? What's the evidence that it's actually space between us that is expanding? Let's look this up. So, why do we say that space between the galaxies is expanding? The expansion of space between galaxies is a fundamental concept in modern cosmology. According to Einstein's general relativity, the universe is not expanding because galaxies are moving away from each other, but rather space itself is stretching. This means that the distance between any two fixed points in the universe will increase over time regardless of the motion of the galaxies. In other words, galaxies are not moving through a pre-existing static space. Instead, space is expanding and galaxies are carried along with this expansion. This intrinsic expansion is not a force that pushes objects apart, but rather a property of the fabric of spacetime itself. The concept of dark energy, which was introduced to explain the observed acceleration of the universe's expansion, further reinforces that the dark energy is thought to be a property of the vacuum energy that drives the expansion rather than a force that acts between objects. The search results also highlight the distinction between the expansion of the universe and the gravitational collapse of objects within it. While gravity causes local clumping of matter into stars and galaxies, the expansion of space is a global phenomenon that affects the entire universe. In summary, but what's the evidence? What is the evidence? You didn't give me the evidence. These are two alternative explanations. Mhm. What news roundup? Eating pets? Debate Google? Oh, debate Google, Telegram, Starlink. This is 1 hour ago. Mhm, mhm.
All right, everybody, welcome to Iran Book Show on this.
Terrible audio. He's traveling and he doesn't get close to the mic. This is maximum volume.
Tuesday, September 10th. I hope you're having a great week. As you can see, still in Barcelona. I apologize for yesterday's show that abruptly ended. I think I continued talking for about another 10 minutes afterwards. If you're interested in what I have to say, it's on the audio only audio podcast. You can do it there. I continue to record, I believe. Sadly, the internet just collapsed. It just died on me right at that point, and I didn't even notice. So I kept on talking. So apologize for that. All the super chat questions from yesterday were saved. I have them, so we will cover them today. So don't worry about me missing one of your questions. We will get to them. We will cover all those super chat questions. Of course, please continue to submit questions for today's show. Let me let's see. I'm just looking at this. Yes, let me just say I don't know what the internet situation is right now, so I don't know how stable it is. For a while, it was fine. For a few weeks, it was fine, and then the last couple of days, it's been giving me problems. So I hope we can get through a whole show today without interrupting, but we might not. It is really out of my control. If it does drop today, I will start a new stream. I'll in all caps say you're gone, you're frozen, or whatever, and hopefully I can see that. I'd appreciate it on the chat. I do glance at that, so I will have an opportunity. So let's hope we can get through everything for as long as we need to today to cover all the questions we're getting today and all the questions, or not, as the case may be. Maybe it's not post. A resident of Springfield, Ohio, from a local resident that who won claimed that's basically post, Facebook post. But yesterday, there was a Facebook post, that basically claimed claimed it was from a resident of Springfield, Ohio, from a local resident that who warns, the post warns, that the author of this Facebook post's neighbor's daughter's friend, I'll say it again, the author's neighbor's daughter's friend had discovered that her neighbors, Haitian immigrants, were trying to eat her cat. She also claimed, this time crediting the Rangers and the police, that similar fates were befalling ducks and geese at the local park. In other words, Haitian immigrants, and there were a lot of Haitian immigrants in Springfield, Ohio, were eating people's pets and even eating the ducks and geese at the local park. This message was clipped, screenshot, and then shared everywhere, all over social media, all over Facebook, all over X, all over Twitter.
Haitians have above average IQ, very smart people, very hard workers, very successful, beautiful women, so very unlikely.
It became, a panic. A number of people started commenting on this. It was picked up by people, of course, on the right, immigrants eating pets, and it just blew up. In addition, somebody made a AI-generated image of Trump defending baby animals from barbarous invaders. You can imagine Trump heroically defending the little baby cats and baby dogs and whatever, ducks, geese, whatever. And this AI-generated image exploded all over the web. As see, this is what happens when you let immigrants, they start eating your pets. I mean, Trump is protecting ducks and kitties. I mean, he can't lose this election. I mean, he's obviously going to win it. Now, the problem is that
this guy hates Trump.
You can look, but there's no evidence that any of this happened. There's no evidence that any immigrant is eating cats. Indeed, there was a woman in Columbus, Ohio, I think, that was caught eating a cat, but she wasn't an immigrant. There are other photos of somebody taking a duck or a goose from the local park in Columbus, Ohio, which is not that far from Springfield. Again, not clear that it's an immigrant.
Not clear that it's illegal. I think you're allowed. Are you allowed to catch a wild animal and eat it? You might be.
According to local police, there are no reports of pets being stolen and eaten, or stolen at all, and no evidence of the ducks and geese disappearing. J.D. Vance, of course.
Geese are disgusting. Geese are so dirty. They poop everywhere. They're huge and they're a little bit dangerous. And so are deer. Deer are not disgusting, but deer are very dangerous. You drive on the highway and you can hit a deer and it, you can die.
Jump in on this. He said, quote, months ago, I raised the issue of Haitian illegal immigrants draining social services and generally causing chaos all over Springfield, Ohio. I commented at the time and did a little research, and it turns out Springfield, Ohio became a magnet for immigrants because Springfield, Ohio was generating more jobs than they could fill. There was a massive labor shortage in Springfield, Ohio that caused them to encourage immigrants. Indeed, the city was encouraging immigrants to come to Springfield to fill the jobs. And Springfield local businesses were benefiting enormously from the influx of immigrants who were working at the jobs that were filled. Now, since then, it could be that this created a certain buzz around immigrants, and some immigrants have come there and have not found jobs, or maybe illegal immigrants have come there, it's not clear, or asylum seekers who it takes a long time for them to get work permits, but who would love to work and where their jobs are in Springfield. So I'm not saying there's no situation in Springfield. There might be. But it's not like immigrants just invaded this place. It's that this place had jobs. They were looking for people, and they invited the immigrants in, and they benefit from it. Anyway, J.D. Vance continues. Reports now show that people have their pets abducted and eaten. By people.
1 second. What's going on with Cenas? Any hope of you joining us today? I need to know. Because otherwise, let's see, Andrew. Hi. Judas, hi. Karen, hi. Who else? Not the best day. Oh my God. Okay.
People who shouldn't be in this country. Where is our border czar? So let's blame this on. Let's blame the non-existent abduction of pets and eating of pets on Kamala Harris. I mean, why not? What the hell? Truth is irrelevant when it comes to political campaigns, and why not vilify a bunch of immigrants and make them look like barbarians? It serves multiple purposes for the right. It serves multiple purposes for the campaign. So again, Haitian immigrants, most of the Haitian immigrants in Springfield are not there illegally. The city, if you go to the city's website, you can find an explanation of that. But it doesn't matter. It doesn't matter. I mean, they'll use any excuse, including false stories, to vilify immigrants, to make a big deal out of an issue that is not.
This guy is pro-immigration, and basically, I am too.
Even real, just in order to win some points with an electorate that seems massively terrified.
Ultimately, I don't have a problem with illegal immigration. That's not the problem. The problem is that we don't allow them to work. So obviously, that's a problem.
Of immigrants, the number one issue on most people's minds, I think, some surveys higher than inflation, is immigration. Why?
Inflation is not a problem. Inflation is a good thing, meaning it's good that we allow prices to rise so that the markets are cleared, so that it gives an incentive for producers to produce more. And in the long term, this will, the prices should fall back if government doesn't interfere. And what caused the inflation, I'm not sure. It could be, I suspect that it was the shutdowns that ultimately caused inflation.
What is it that immigrants are doing to you? 90% of Americans don't even interact with immigrants. It has no impact on their lives, and yet this is the number one issue affecting everybody's lives. Yeah. Eating cats. That's where we are today. Fake news all over the place. I wonder what the authorities are going to do about the fake news that is going on. I wonder if eating cats is going to come up in the debate tonight. So as you probably all know, because it's broadcast everywhere, the Kamala Harris and Donald Trump are going to be debating tonight. What exactly are they going to be debating? And What?
Okay, I don't know. What else? Let's see what we were looking into. Yeah, maybe we should look into this least action principle.
Rock has a certain kinetic energy and it has a certain potential energy. So for kinetic energy, I'm going to write T as a function of time. Right? It's changing its velocity as a
So
certain
let's see what he
action
says.
in the accelerator. So these are vectors. This is a vector equation, and we can use it to find the acceleration at each point if we know the force at each point. And using the acceleration at each point, we can find the position at each point in time. But in this video, we're going to talk about a different way to do that. So we're not using Newton's second law. We're using something different. And the thing that we're going to talk about in this video is called the principle of least action. So least action. Least action. What is action? Well, at each point along this path, along every path, but at each point, the rock has a certain kinetic energy and it has a certain potential energy. So for kinetic energy, I'm going to write T as a function of time. Right? It's changing its velocity with time, so its energy due to its velocity will also change with time. And then its potential energy, which I'm going to use the letter U to represent, is also a function of time.
So T is kinetic energy?
Kinetic energy, I'm going to write T. Least action. What is action? Well, at each point along this path, along every path, but at each point, the rock has a certain kinetic energy and it has a certain potential energy. So kinetic energy, I'm going to write T as a function of time. Right? It's
Okay, so he's throwing the rock up and then the rock comes down. And this is the height of the rock. And this is the time. So at T1, the rock went up. And at T2, it finally came down. So what does this path look like? So it could look like the red path, or like the squiggle, or like the this one, or the shallow one. So how can we know? How can we predict it? Okay. So he says he's going to use the least action to figure it out. So the kinetic energy is going to call capital T at time t.
changing its velocity with time, so its energy due to its velocity will also change with time. And then its potential energy, which I'm going to use the letter U to
Okay, so this is the energy due to the velocity, and this is the energy, I guess, due to the height.
represent, is also a function of time. Right? It's moving through this gravitational field and it's changing its potential energy. At each point along the path, there's a potential energy and there's a kinetic energy. And if we want to write it for this particular situation,
Right, so over here, there's high kinetic energy and lower potential, and there's an exchange. Over this path, at this point, all the kinetic energy has been exchanged in return for a potential energy. And then the potential energy is returned back into kinetic energy.
we would write 1/2 mv squared for the kinetic energy of the
So kinetic energy, the equation for kinetic energy is 1/2 mv squared. He doesn't explain why.
rock. And then since it's in a uniform gravitational field, we would write for the potential energy mass times the acceleration due to gravity.
Why is it 1/2 mv squared? Let's try this guy.
Now say we want to describe the motion of the ball from the time. One reason is probably that the basic ideas behind when people are first introduced to classical mechanics, it is usually in the spirit of Isaac Newton. One reason is probably that the basic ideas behind Newtonian mechanics seem to make a lot of intuitive sense. A net force acting on some object gives it an acceleration proportional to the force. No net force.
Yeah, it's very intuitive, but not clear why. Why is F equals ma? Why not F equals m cubed square root of a
means no acceleration.
times 5?
And two objects interact with each other through equal but opposite forces. These force laws are easy enough to state and usually straightforward to apply to simple problems, but they often prove to be difficult to work with when considering more complex systems. Enter Joseph Louis Lagrange, who formulated his own version of classical mechanics in the late 1700s. The purpose of his work was to provide an alternative to the Newtonian approach by describing physical systems in terms of energy rather than forces. The idea behind this video is to introduce the fundamentals of classical Lagrangian mechanics. We will discover where the Lagrange
Nikocado avocado astonishing weight loss. Michael Schellenberg. America's cultural crisis. What's collapsing? Is civilization collapsing? Trump attacks voters. David Pacman. Starship Test Flight 5 delayed until November due to FAA regulations. That is terrible. That is absolutely terrible. Absolutely terrible. We'll take a look at it after.
Function comes from and how it can be interpreted.
So let's look at Lagrange. What did he say?
Introduce the fundamentals of classical Lagrangian mechanics. We will discover where the Lagrangian comes from and how it can be interpreted.
So the Lagrangian is T minus V, the kinetic energy minus the potential energy.
We'll also find out what the principle of stationary action means and how it gives rise to the Euler-Lagrange equation. Although our approach will be intuition-based, we'll be using tools and ideas from several different areas of math, including multivariable calculus, linear algebra, and ordinary differential equations. So in order to get the most out of the video, it helps a lot if you're reasonably familiar with these subjects. But with that out of the way, let's get started by performing a simple thought experiment. Imagine that we're holding a ball at some initial height y0. At some moment in time t0, we throw the ball straight upward with some initial speed v0, such that the resulting trajectory is one-dimensional. Now say we want to describe the motion of the ball from the time it leaves our hand at t0 until it returns at some simple thought experiment. Imagine that we're holding a ball at some initial height y one-dimensional. Now say we want to describe the motion of the ball from the time it leaves our hand at t0 until it returns at some later time t1. Let's start out with the Newtonian method. We first reset the system, then throw the ball again, but this time freezing it in midair. If we ignore air resistance, we only need to consider the gravitational force, which has a magnitude equal to the mass of the ball m times the gravitational acceleration g. We then write down the appropriate force law, here with the acceleration written as the second derivative of the position with respect to time, signified by the double dot notation. We proceed to solve for the acceleration, which is just negative g, like we expect. This is now a second-order ordinary differential equation in time, which we can simply integrate to obtain the velocity function.
1 second. This is, I guess, Newtonian. 1 second. There's a message. La 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 la. Oh my god, no, I cannot take the call. Cannot take the call. 1 second. Okay. Mm-hmm. Okay, we're ready to go. La 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 la. All right. So this is Newtonian, I think. He didn't say, but I think he's doing a Newtonian analysis first.
But with that out of the way, let's get started by performing a simple thought experiment.
It's a thought experiment, okay?
Imagine that we're holding a ball at some initial height y0. At some moment in time t0, we throw the ball straight upward with some initial speed v0, such that the resulting trajectory is one-dimensional. Now say we want to describe the motion of the ball from the time it leaves our hand at t0 until it returns at some later time t1. Let's start out with the Newtonian method.
Right, let's start out with the Newtonian method. Okay.
We first reset the system, then throw the ball again, but this time freezing it in midair. If we ignore air resistance, we only need to consider the gravitational force, which has a magnitude equal to the mass of the ball m times the gravitational acceleration g.
Okay, so it's negative mg. G is a constant.
We then write down the appropriate force law, here with the acceleration written as the second derivative of the position.
Okay, so the total amount of forces, which as far as we know is negative mg, is equal to my double dot, the mass times acceleration, if we assume F equals ma. Okay, we'll assume F equals ma just for Newtonian mechanics. Later, maybe he'll tell us where it comes from.
Position with respect to time, signified by the double dot notation. We proceed to solve for the acceleration, which is just negative g.
Okay, so y double dot is, I guess we can divide both sides by m. So it's just negative g. So the acceleration as a function of time is a constant. It's negative g.
Like we expect. This is now a second-order ordinary differential equation in time, which we can simply integrate to obtain the velocity function.
So y dot of t is just the integral dt, because this is dy squared dt squared, or d squared y dt squared. So this is just dy dt, and one dt came over, and we integrate both sides. He didn't show the integration of the left side, that's fine. So it's the integral of negative g dt, which is just negative gt plus c. Okay.
We also remember what the system looked like at the initial time t0, which we for all intents and purposes can set to 0. We then recognize that the constant of integration must equal v0 in order to satisfy our initial condition for speed. The velocity equation is then just the first order ODE, which we integrate to obtain in order to satisfy.
So why is c v0? He didn't explain. So at t equals 0, the velocity was v0. So when t is 0, all you had is c. So c is equal to v0. And that's the reason. Okay.
Our initial condition for speed. The velocity equation is then just the first order ODE.
1 second, let me check. There's no one watching. Okay, yeah, maybe we should just say that that's what we're studying. If anybody wants to join us to study, let's listen to the news a little bit.
What exactly are they going to actually say? What values are going to be? I mean, really, the only value of this debate is to see how they handle each other. Can Kamala stand up to Trump?
Oh, when he said debate, that's what he meant. Okay.
Can she?
He has 38,000. I remember when I first started following him, he had 35,000.
Oh, it's all about personality. The one thing that won't be discussed today.
He has this theory that anyone that votes for Trump is because of Trump's personality. I don't know why he keeps saying that. He has no evidence. He never presents any evidence that people who vote for Trump do it because of Trump's personality. I don't know why he keeps saying that. He never showed any evidence.
Are real issues. The things that won't be discussed today are real solutions. The real things that won't be discussed are the real problems that this country faces. None of that will be discussed. I mean, it might be raising a question, but you can guarantee that Donald Trump and Kamala Harris will not respond to those questions.
I mean, he agrees that there are actual issues that people believe in. People believe that immigration is bad. That has nothing to do with Trump's personality. People vote for Trump because he says immigration is bad, and people believe immigration is bad. Therefore, people vote for Trump. It's not Trump's personality. So he knows people don't vote for Trump because of his personality, but he always defaults to that, and he accuses people for doing that. I don't know. It's like he suffers from Trump derangement syndrome really, really badly. Very, very unfortunate, because he is the best guy in the world that I follow. He's the least deranged of everyone I know in the world. Very unfortunate.
This is all a personality contest. One way to.
That is such nonsense. I don't think anyone likes Kamala. I don't think anyone likes Trump. It's the issues. I don't think anyone agrees with everything with Kamala. I don't think there's any one person that agrees with Trump on everything. It's, it's a representative democracy. I don't know why he takes it so hard.
Said that the key to tonight is who can convince American people that if they get elected, they won't destroy America. Because both parties are saying, Trump is basically saying, if Kamala's elected, America's over. It's finished. It's history. It's gone. We won't survive. And the Democrats are saying, if Donald Trump's getting elected, it's over. It's finished. America won't survive. This is the last election you'll vote in. It's all gone. And I think a lot of American people are skeptical about both those claims, but partisans on both sides are committed to them. And maybe what you need to convince American people tonight, if you're Donald Trump or you Kamala, is no, the country will survive me. Although I doubt that is on their minds, and I doubt that'll be the strategy. It's going to be, I don't know. I guess it's going to be interesting. It's going to be horrible. At least it won't be a complete embarrassment like Biden was. I think Kamala will do a lot better than Biden. At least that. But whether she can actually change anybody's minds, I mean, the only way she can do that, and it'll be interesting to see how she plays this, because she hasn't been successful so far. For Kamala to win, and right now the polls basically show it being a toss-up, right? It's a complete tie. It's a tie in the popular vote. It's a tie in every one of the battlefield states. If you believe that the polls are still biased against Trump, then maybe that tie suggests he has an advantage. But certainly it does not look like Kamala's going to run away with it like some people were projecting just a week ago, 2 weeks ago. It does not look like it's going to be a slam dunk either way, like it looked like it was going to be for Trump when Biden was running. It looks like this will come down to the last votes in those 7 swing states, and this election will be decided by a few tens of thousands of people, probably independents, maybe moderate Republicans, who decide whether they're going to vote for Trump or whether they're going to vote for Kamala. They're going to vote against Trump, because I think that'll be their primary. And the question is, what would get them to vote one way or the other? What would get them to go in one direction or the other? It's not going to be a policy issue. Nobody cares about policy. The voters don't seem to care about policy. It's not going to be anything particular.
And then he goes again. Nobody cares about policy. It's like nobody cares about policy. So what are you talking about? Everyone cares about policy. You talk to people. You cannot change anyone's mind. Everyone has a very rigid position on every policy. What are you talking about?
So what does Kamala have to do to convince Americans that she should be elected? I think it's simple. It's easy, and she could do it. She could do it early in the debate, and she could do it powerfully and strongly. And I think it would be a winning strategy. And that is to convince Americans that she is a centrist, that she repudiates her own legislative agenda from when she was a senator. In 2019,
But she doesn't. She now wants to do price control.
when she ran for president, when she ran in the Democratic primaries, she ran as a representative of the crazy left. Americans would not elect that Kamala Harris for president.
Because that's what she is. She's now suggesting price controls. She is a crazy leftist.
The United States. If she is going to win this election, she has to convince them, the American people, that she is to the right of Biden, that she's a centrist through and through. That to do that, she is going to come out and say, look, I've now been vice president for 3.5 years. I understand a lot more about how this government runs and how this country runs. And it's clear to me that to govern this country, I must govern from the center. That some of the policies that I had back then, for example, my opposition of fracking, was a mistake. This country needs energy. And therefore,
Are you kidding? These people are anti-energy. These people are green through and through. You want to actually, he likes, that is Trump. You're mixing Trump with Kamala. Oh my God.
must frack, which she has said she has changed her mind in fracking, but she needs to make it explicit. And she needs to maybe take 1 or 2 other positions she had back then and say, I no longer hold these positions. I am now committed to X, Y, Z, whatever she believes the center is. I think that's her strategy. It should be her strategy. I don't think it will be. I don't think she's brave enough. I don't think anybody in the campaign is brave enough to do something like that, but that should be the strategy. And I think she wins if she does that. Trump's strategy is different. and I don't know if it's possible for him to execute. Publius says, you're a dreamer. I can dream. Let me dream. What the hell? Trump's strategy is to come across as sane. And I mean, again, if he wants to win, and if he's rational, which I think he wants to win, but I don't think he's rational, it's to come across as...
I don't think he's rational. Yeah, Trump is not rational. Yeah. This guy denies the rationality assumption.
Sane and positive and inspiring in his pro-Americanism. Yeah, I mean, you can talk about the evil of the border, and you can talk about the evil of inflation, and say stupid things about both things, because that's what he does. He says stupid things about both the border and primarily about inflation, which he has no concept of what it means. But if he can stop whining about the 2020 election, which he doesn't seem to be able to, at least not in his tweets, if he can present himself as, sane and reasonable in some way, then I think he has a chance of really taking the lead after this debate. It really is a toss-up. Either one of them could score major progress in this particular debate that moves them forward, that takes them and gives them the win. It's not going to take much. It's about convincing a few tens of thousands, maybe 100,000 people, either to switch where they are today or to go out and vote for you. And that should be doable for both of them. They just have to come up with the kind of right strategy. I mean, they're both going to talk about taxes. Kamala Harris will talk about raising taxes, but not raising taxes on the middle class. She's going to accuse Trump of raising taxes on the middle class with his tariffs, which is absolutely a legitimate criticism, because it's absolutely true. And if she's smart, she hammers him on tariffs. Hammers him on it. Now, of course, she might be coming at it from a weak position.
I'm pro tariffs. I mean, if we can reduce the income tax, maybe completely remove the income tax, and instead the government should get everything from tariffs. The idea is that it's better to tax consumption, which is tariffs, than to tax income, which is production. So I think it's better to tax consumption rather than tax production, because we're going to have it's going to strengthen the economy. It's going to improve investments, and so we're going to have a lower quality of life in the near future, but in the long term, it's going to give us a more robust economy. I think it's a good idea. What's this? From core memory to the internet, the amazing history of the PDP-11. Yeah, the PDP-11 is an incredible machine, from what I heard. Used to be an incredible machine.
Biden has basically kept all of Trump's tariffs. But Trump's new proposals on tariffs, what is the technical term? They're completely wacky. They're insane and unbelievably disruptive.
No. What's your evidence? This guy is an economics professor, a finance professor. He knows his stuff, but ultimately, I think he's wrong. Well, he has positions that he never supports with any evidence.
To the U.S. economy, and she could just hammer him on tariffs. That.
No, she can't. You can't. No one can. Tariffs are better than income tax. If you have two alternatives, tariffs or income tax, tariffs are better.
I think would at least get him upset.
I mean, any tax on consumption is better. Any tax on consumption is better than any tax on production. That's my intuition. You're going to have to convince me that I'm wrong.
And I think that's what she needs to do. She needs to trigger him so that he shows his true self, which is an unhinged Trump.
He's not unhinged. What are you talking about? He's never, ever been unhinged. He was shot at and he didn't go berserk. He didn't do anything. He responded like a grown, like an adult. He's always an adult. I don't know what you're talking about. Unhinged. You're unhinged.
She needs to, if I were her, I would have a few things there about Trump being a loser. Remember, I suggested that to the Republicans in the primaries. They never did it, of going after him as a loser.
He's not a loser. What are you talking about?
It would definitely, if I were Paris, I would go after Trump. He's a loser. And he's a whiny loser. He's a bad loser. He's a loser that can't accept defeat. And I would go after him on
I don't know. I mean, the fact that he keeps harping on losing because the election was stolen, I agree that the election was stolen, but not in the way that, not with votes. The election was stolen because there was so much interference from the elites, from the institutions, from the FBI, from the newspapers, from social media, everything. The entire apparatus, the elite apparatus, came after Trump and came to support Biden. So, in that respect, yeah, the election was stolen. I agree.
tariffs that American people.
That's a stolen election, basically. So, Trump received counsel that is stolen election and he can suspend the Constitution. And that's completely understandable.
Tariffs, and every economist in the world agrees on this, and Trump is lying.
1 second, there's a message. Okay.
And deceiving the American people by pretending and deluding them into thinking that foreigners pay for these tariffs. Those are the lines that she needs to take. She needs to be tough with him and assertive.
It's not important that foreign governments are paying or foreigners are paying. That's not important. It's better always to tax any consumption than to tax any production. That's my intuition. You have to prove me wrong.
And she needs to, cause him to go unhinged. And
no, he's never been unhinged ever. I don't know what you're talking about.
And that's possible. That's very possible to happen. I mean, there were moments even
no, it's impossible. Stop wasting your time. This guy's unhinged.
With Biden, when Trump was a little unhinged, and Biden was not saying anything intelligible, at least. Kamala Harris has finally published an issues page on her website. So now we have an actual agenda. It's a typical politician's agenda, so it's kind of meaningless, and it's got mostly things that we know: tax cuts for the middle class, subsidies for first-time homebuyers, federal ban on corporate price gouging, whatever the hell that is, for food and groceries, and a bunch of other
those are terrible policies.
Things that's supposed to rebuke Project 2025. She'll try to latch 2025 onto Trump. I don't think that's going to work. Nobody knows what 2025 is. It worked a few weeks ago. Enough. Move on to something different. So nothing really exciting on the issues page. But at least she can now say, I'm not content less, as people were claiming she was. So that's a debate. We'll talk about it more tomorrow. I'm not going to watch it live because it'll be early morning here in Barcelona, and I certainly will not be waiting up in order to watch it. If I were, I think that I don't know what's going to happen with the abortion topic. We'll see. I mean, maybe Trump will be asked some kind of cornering, some questions about abortion to corner him, where they try to corner him because.
So Trump is now pro-abortion, which is great.
He's obviously come out with very relatively liberal views on abortion. That has alienated his base. It's caused him to have to change his mind, overturn something he said from one day to the next about abortion because the base was so alienated by what he said. Those inconsistencies.
Why are you discussing Trump's policies? I thought it's all about Trump's personality.
Something that can be brought out. It'll be interesting to see how foreign policy plays into this. And again, it's hard. Kamala, unfortunately for her, rambles. So if she can become a prosecutor for this debate and give short, succinct, powerful, strong, emotional, evocative answers, again, I think she has a chance of winning. But it's hard to tell how these things go, and it's impossible to tell how the American people understand these things and what they get or don't get out of it. Right? Over the past month, Trump has been. I mean, he's just nuts.
What are you talking about? He's not nuts. What are you talking about?
He shared a post on his Truth or Twitter calling for former President Barack Obama to be subject to a military tribunal. He's reposted fake images of well-known Democrats clad in prison grab. He's threatened Mark Zuckerberg with a life sentence for helping state and local governments fund elections in 2020. Just a political contribution, but he's going to put Mark Zuckerberg in jail. He has basically said that if anybody,
That's not unhinged. That's in his view defending the Constitution. That's his job.
is caught cheating in this election, if there's any election manipulation, if there's anything, the people are going to go to jail for life. They're going to go to jail for a long, long time. They're going to, fully stay.
Yeah, that's his job. That's the way he sees his job. You don't like it, don't vote for him. But it's up to the American people. That's called a democracy.
I mean, really, go after them. When I win, those people that cheated will be prosecuted to the fullest extent of the law with those long-term prison sentences, so that this depravity of justice does not happen again. In other words, he's saying, I'm coming after you guys. I don't know to what extent this is going to intimidate, particularly if it's a close election, if this intimidates election officials all over the place. I mean, he's completely unhinged.
No, that's his job. No, he's not unhinged. He believes that's what happened in the previous election, and it's fine. He's not unhinged at all. You can disagree with him. That's all.
Police officers to watch for voter fraud at polling places because voters are afraid of that badge and they might not commit fraud if you're there. He's threatening people left and right and using bloodier, more violent terminology over time. I mean,
that's the way he sees his job. You don't like it, don't vote for him. It's fine.
He's becoming more and more unhinged over time.
He's not becoming any unhinged ever.
And I think
you're becoming unhinged.
The scariest thing about this election is that it is close and that Trump just does not accept that he's lost. Does not accept it. And a lot of the people in places like Georgia who manage the election process this time around are Trump people. The same in, I think, Wisconsin and Michigan. It could very well be this time, whereas last time election officials had integrity and basically went with the facts and refused to change their minds and refused to do illegal things at Trump's behest. This time,
it's not illegal. It's people defending the Constitution. It's, that's the way they see it. At the end of the day, you swear personally to defend the Constitution. So it's up to you. It's up to each and every American to defend the Constitution. That's the nature of the beast. You don't like it, you don't have to live here. It's fine.
Nobody's going to stop it because the people in these different election committees in swing states are all beholden to Trump. So this election...
No, they're beholden to the Constitution. No one is beholden to Trump. Stop the nonsense.
It could be very, very ugly. It could go to the Supreme Court. Wouldn't be surprised if this was a close election, if ultimately the Supreme Court had to decide it. It could be violence. It could be violence from either side.
This country was created on violence. It's fine. Don't worry about it.
Left pissed off if Trump somehow wins on a small margin. The right pissed off if the left somehow wins in a small margin. This election is maybe the most unpredictable election I can remember in terms of the outcome. Not of who actually gets elected. I think it's a toss-up, but on whether the election is acceptable and kind of what the results are, how it plays out. I can't think of an election. In advance, we know that this is going to be a real disaster. Again, Trump already intimidating people. It'll be interesting to see if Trump gets asked in the debate about federal spending.
All he's saying is that he is going to defend the Constitution as he is sworn to do. That's all. You don't like it, get out.
And budget deficit. It's important to note, and I know many of you don't like hearing this, but it's important to note that federal spending increased by more during Trump's 3.5 years, so pre-COVID. So before COVID, the 3.5 years of Trump's presidency, the federal spending increased more than it did during 8 years of Obama.
Yeah, Trump is terrible. I agree. But you said that it's not important. No one votes for Trump based on policy. It's all personality, no evidence. But I agree. Trump is terrible. But I would still prefer Trump over Kamala. She's more terrible.
So it's a real good question about who's really responsible for inflation and the debts and all that stuff. You can blame it on Biden, but certainly Trump has some responsibility for it.
Yes, Trump. It's Trump's inflation. I agree with that.
Okay. Anyway, it's going to be an interesting debate. We'll talk about it tomorrow. I'll watch it after the fact. We talk about it and comment on it. So I'm interested in what you guys think if you're going to watch it live. But it's going to be ugly and uninteresting in some regards and fascinating in other regards. This all got messed up. All right. Let's talk a minute about Europe. we've talked about this quite a bit over the last couple of years, particularly more recently in that Germany's in recession and European economy is struggling, and there's very little tech in Europe, very little tech entrepreneurship in Europe, and Europe is falling behind. If you look at, let's see if I can find these stats. I had some interesting stats here. Yeah, I mean, basically the United States, by every measure, is dramatically outperforming Europe since the Great Financial Crisis. Over the last 15 years, the United States stock market, US GDP per capita, income, wealth, but every parameter, individual Americans and the American economy in aggregate are performing way better, dramatically better than Europe. Right? And a big part of that, obviously, is that the United States has Silicon Valley, and it has entrepreneurship, and it has new companies being born, and it has innovation happening. And Europe is lagging. Europe is dramatically lagging behind in tech and in innovation and in anything new, in biotech and in everything. And its GDP is hurting, and it's basically been stagnating for 15 years. Nothing has gotten better. I mean, except in countries like Greece, which fell off a cliff and have recovered quite nicely. But that's an exception. The European Union as a whole has done pretty badly. Again, some Eastern European countries like Poland, Lithuania, Czech Republic, Slovenia have done very well. But again, exceptions. Western Europe, flat. 15 years, barely any growth. Anyway, they appointed a commission. That's what you do, right? You appoint a commission to figure out what's going on. And, the commission was headed by Mario Draghi, who was the former president of the European Central Bank. And I think he was even prime minister of Italy for a while. Anyway, Draghi came back yesterday, with his report. And basically said, look, Europe can compete. It's losing. It's way behind on investment. It's way behind on tech. It's way behind on innovation and all these parameters. And the European Union needs to get its act together. Energy prices are through the roof, primarily because cheap Russian gas is no longer available, and because the Germans shut down their nuclear power. And yet, all these countries committed to going to net zero, whatever that means. And so his report basically says, look, you can't do this unless there are dramatic changes at the EU level, and that means a significant reduction in regulation and massive public investment. Now, I think public investment is a huge mistake, but he's talking about investing
Public investment, he means government investment? That's terrible.
$900 billion a year in sectors like technology and defense, in regulation.
Regulation is good.
And massive public investment. Now, I think public investment is a huge mistake, but he's talking about investing $900 billion a year in sectors like technology and defense. So his solution is half good, deregulate, and half bad, increase public spending. If Europe was really serious about this, if Europe really was committed to competing with the United States and China in terms of technological leadership and innovation, I mean, Europeans are educated. They have the potential, the knowledge. There have been periods in European history where they've been incredibly entrepreneurial. They can produce, they can create, they can build. They've shown that in the post-World War II period. They showed that.
So I'll tell you what they're going to do. They're going to do the investment part. They're not going to deregulate. It's too dangerous because politicians are just too afraid.
In the 19th century, with the amount of innovation and economic growth that was going on in Europe at the time, what the European Union needs to do is get out of the way. What they need to do is find ways to stop. They need to just not find ways. They just need to stop getting in the way of entrepreneurs. They need to, again, deregulate, reduce taxes. I don't think the European Union taxes, but you can make recommendations to its members and just create an environment as friendly to entrepreneurs, to innovation, to business, to progress, to creation, to building, to making as possible. They have done the opposite for 20 years now. They have built a massive bureaucracy that makes it more and more it's made it more and more difficult to start a business, to innovate, to build, to construct. And then they need to embrace the fact that they're going to be dependent on fossil fuels for a long time and build even more LNG terminals all over Europe so that they can import natural gas from the United States and the Middle East and wherever to drive down the cost of energy. Natural gas is incredibly cheap, even transported on a boat through LNG. It is incredibly cheap.
Yeah, but they're terrified of Greta. Greta will become upset. And Greta is not a joke. Greta is an international terrorist. So they're terrified of her.
And start, as the French have already, start a campaign of building next generation nuclear power plants. France is on that track of building nuclear power plants. It could be in a position in a few years to provide energy to the rest of Europe. Scandinavia is building nuclear power plants. Germany is holding out. But that's what they need. They need to abandon all this money going to, again, what do you call it? Solar panels in Germany, which is funny. And, you can understand solar panels in Spain, particularly southern Spain, where it's sunny almost all the time. Solar panels in Germany doesn't make any sense. Windmills, and invest in what's cheap, and ultimately invest in the cleanest energy available, which is nuclear power. And I think pretty easily to say, the safest. Next generation nuclear power will probably be, by far, the safest source of energy possible. So reduce the cost of energy and deregulate.
Yeah, Greta is not going to allow that.
Those are two things that Europe needs. Now, they do have one other problem. And I'm not sure how you solve this. This is more of a philosophical problem, more of a sense of life problem, more of a spiritual problem that they're going to be challenged. And that is, how do you change the mentality of Europeans? Too many Europeans are unambitious. The spirit of entrepreneurship, the spirit of going out and making something of your life, of building, of creating, of that, it just is diminished in Europe. They're much more focused on how many vacation days they can squeeze into a year, and how much time they can get off, and life-work balance, but where the balance is way away from work. Now, some of that is going to hit them ultimately when some of the governments suddenly discover that they can't afford to pay for all this time off, they can't afford to pay for all the pensions, they can't afford to pay for the early retirements, they can't afford to pay for all this healthcare. But some of that they might want to start thinking about how you change the mentality of young people, how you get them to be more ambitious, how you make them less reliant on a pretty efficient welfare state relative to America. It's a very efficient welfare state. That's going to be a challenge. So throwing $900 billion a year into sectors like technology and defense, I mean, I understand defense, they need to make the investment in defense because of Russia, but technology, I think, would be a massive mistake. And
it ends up that Putin is going to save Europe because Europe is going to have to wake up. As long as Putin keeps attacking and keeps threatening and keeps being militant, that's going to end up forcing Europe to stop being so green and get its act together, maybe.
And
or maybe Putin will take over Europe, and that's also a solution.
The money and reinforces the central planning mentality the Europeans have too much of already. What they really need is to create an environment in which private capital, venture capital, wants to come and invest in European companies. And most venture capital doesn't want to invest in European companies. And even European companies that are successful, there's so many regulations and constraints that it's very hard to become a big company in Europe, a big tech company in Europe. I mean, Europe presents barriers to American tech companies in Europe, never mind to its own companies. All right, so the drug report was published yesterday. I think the only impact it's probably going to have is to get the European Union committed to subsidizing and in quote investing even more than they are right now, which is wasteful, and it probably will lead to even more stagnation. Good news. Good news these days when it comes to economics and when it comes to politics only comes from one country, basically one country.
The United States.
And that's Argentina. Because in Argentina,
oh yeah, Milei.
You actually have a president who has a clue, more than a clue, has an understanding of economics, and is actually trying to run the country to the best, I think, of his ability, or to the best of what his parliament will let him do, in order to improve the livelihood, the standard of living, the quality of life of the people of Argentina. Some good news out of Argentina. It turns out that Argentinians are taking the dollars they have out of the mattress. So Argentinians over the last few years have been converting their pesos into dollars on the black market. So horrible rate, much different than the official rate, but they can't convert a lot of dollars, pesos into dollars by the official rate. So they're doing the black market. And they've been putting it in the mattress. They have been taking it out of circulation, and they have basically been encouraging this massive black market to exist. So they keep it in the mattress. In the mattress, that money does not create any economic activity. And indeed, it takes dollars out of circulation at a time when dollars are needed in Argentina to import things from other countries where you use dollars. So it seems that Argentina has become so confident in Javier Milei and his policies, and he's also promised a tax amnesty for people who bring the money out of the mattress, that they're actually taking it out and depositing the money in banks, in dollar-denominated accounts in the bank. Dollar deposits have surged 40% since Milei took office. They now sit at close to $20 billion. This is the highest level they've been at since late 2019. So in the meantime, Argentinians are still paid in pesos, but they can open a bank saving account at a bank in dollars.
That's incredible.
More and more are doing so, but more importantly, they're taking those dollars out of the mattress and putting them in the bank. That means they trust the banks. They trust the government not to confiscate the dollars. They trust the government not to tax these dollars that suddenly showed up from the black market. This is one more step in the process of Argentina doing away with all capital controls, which is crucial for its economic health. That is one more step to getting the Argentinian economy closer to what Milei promised, which is dollarization, which would completely revolutionize the economy, put it on a ballot, get rid of the central bank, and I think put Argentina on a path that could potentially make it a really, really strong, powerful economy, particularly if Milei can continue to deregulation, continue to shrinkage of government spending, and everything else that he's done. So tax amnesty expires September 30th. So people have until September 30th to take the money in the mattress, put it in the bank. I expect that to spike even further. I'm sure a lot of people will keep some money in the mattress because you never know. And that's probably good policy in Argentina. I mean, who knows what will happen with Milei, to Milei. So you want to have some cash. But it's great to see the confidence they have in him, in his programs, and the confidence in the future of the Argentine economy, which I think this represents that confidence. So it's going to be interesting. I mean, basically, from the moment Milei takes the office, dollar deposits in banks have been going up. Just one more sign that the Argentine economy, Argentinian population is supportive of Milei's agenda, and that he's doing the right thing. All right. Let's see. Oh, one thing both it looks like both Trump and Kamala will agree on tonight, if it ever comes up, probably won't. They both agree that a Japanese company, Nippon, should not be allowed to buy U.S. steel.
Oh, terrible. Why?
Nobody can explain exactly. U.S. steel should be owned by the U.S. It's in the name, after all. Japanese owning U.S. steel, it's strategically bad. It's a national defense issue. Biden administration literally is going to block it. I don't know what excuse they're going to use, but the government can stop a merger, and they're going to stop Nippon Steel from buying U.S. steel, which is not good for U.S. workers. It's not good for U.S. steel. It's not good for anybody. It's just they're playing to, I don't know, some xenophobic something that voters might, I don't know. It makes zero sense. The Democrats maybe are responding to the union, the steelworkers union, that may be worried about I don't know, losing jobs, but they're much more likely to lose jobs if U.S. Steel stays an American company than if they bring efficiencies, increase productivity, increase markets that Nippon Steel provides for them.
Oh my God. Okay, let's see what's going on. Let's see, where were we? This guy.
Which we integrate to obtain the position function, this time recognizing the constant of integration.
Okay, so the next step in the
Zero.
integration.
We then recognize that the constant of integration must equal v naught in order to satisfy our initial condition for speed. The velocity equation is then just the first order ODE, which we integrate to obtain the position.
So the next step is the actual displacement equation. So the height or the position in the y-axis at time t is the integral, right? We're integrating both sides. So this is dy dt. So we're taking the dt, moving it over, and integrating both sides. Integrating dy becomes y, and this is the dt. Okay, so this is like 1/2 gt squared and vt.
Function, this time recognizing the constant of integration.
So negative 1/2 gt squared plus v naught t plus an initial condition we know at t0, y0 is y naught. So y naught is equal to y naught, to the constant.
Integration as the initial position, which we can also set to 0 in order to keep things simple. These equations are now the equations of motion for our system, and they provide a complete description of how it evolves in time and space. The last one is perhaps the most relevant, as it represents the actual space-time trajectory of the ball. This result,
and here we see that it's a parabola.
Probably seems a bit trivial, but it is meant to provide a concrete example to keep at the back of our minds, as we now start developing the Lagrangian method for obtaining the equations of motion. This means that we move on to consider energy. We can readily write down the well-known expressions for the mechanical energies. The kinetic energy, here called T, which is a function of the ball's velocity, and the potential energy B, which is a function of its position.
So he says that the kinetic energy is a function of velocity. Really? That's interesting. And the potential energy is a function of the height. But he doesn't derive these equations.
If we plot these energies against time, we get two curves which seem to be mirror images of one another with respect to some symmetry line. This
Wait.
But it is meant to provide a concrete example to keep at the back of our minds, as we now start developing the Lagrangian method for obtaining the equations of motion. This means that we move on to consider energy. We can readily write down.
Wait, so he took the conclusions of the previous discussion, the Newtonian equations.
Well-known expressions for the mechanical energies. The kinetic energy, here called T, which is a function of the ball's velocity, and the potential energy B, which is a function of it.
So this is 1/2 mv squared. Okay, and this is mgy, okay, or mgh.
Position. If we plot these energies against time, we get two curves which seem to be mirror images of one another with respect to some.
Okay, this is just energy. So the total energy is constant. So the potential energy is mg as a function of y, but y as a function of t. So this is as a function of t. So he doesn't show the complete expression. This is mg times y, whereas 1/2 mv squared, where v is gt. So this is 1/2 m gt squared. So it's g squared. It's okay, it's some constant, but it's times t squared, or negative t squared. So the kinetic energy, he doesn't say which color. Oh, this is the kinetic. No, this is the green is kinetic. So the kinetic starts high, is 0, and ends high, and the potential starts at 0, and it's halfway. It's the highest, and then low. Okay. So the kinetic energy starts high, right? So these two are mirror images. That's what. But he doesn't have any. He doesn't show. I mean, he doesn't expand this equation. He doesn't expand this equation. I would at least expand them and show that this is just a function of t squared or negative t squared, and this is a function of y is negative t squared. So this is, so the potential energy is negative. It's an upside down. And this is y squared. So this is positive because it's negative gt squared. So it's positive g squared t squared. So it's a right side up. He should add them both and see that they come out to a constant. The t doesn't show up. Should not be a function of t.
Symmetry line. This symmetry is due to the fact that the total energy is conserved, such that the potential and kinetic energies are always being converted into one another at equally great but opposite rates. Applying these curves against the same energy.
How does he know this? How did he get this?
B, which is a function of its position. If we plot these energies against time, we get two curves which seem to be mirror images of one another with respect to some symmetry line.
What do you mean seem to me? What's your evidence? What's your proof? I mean, why are you hand-waving so much?
This symmetry is due to the fact that the total energy is conserved, such that the potential and kinetic energies are always being converted into one another at equally great but opposite rates.
What's your evidence for this? You need to show that dv dt is equal to dt dt, or the negative. What's your proof? So the derivative of this is the derivative of this. It's difficult to see that they're derivatives of each other. So this is, the 2 goes down. So this is just, the derivative of this is just my dot, which is just this times m. It's just m times this. So it's m times negative gt plus v naught. And the derivative of this is just mg. Well, the derivative, wait a minute. No. This is, no. No. The derivative with respect to time. The derivative of this with respect to time is the derivative of this times the derivative of this with respect to time. Derivative of this, I mean, we need to employ the chain rule. So we need to replace y dot with this and y with this. And after we replace it, we need to take the derivative. So the claim is you end up with the same equation. So this is m times this. Okay, and this is mg times this. You end up with g squared. And here you end up also with g squared. So you already see that there is a g squared in both. Okay, so he says they end up being the same except for the negative sign. This becomes positive, but this remains negative, I guess.
Applying these curves against the same energy axis doesn't actually tell us the whole story, since even though t and b both have units of energy, they are fundamentally different quantities, one related to speed and the other to position. So how could we treat these energies on more equal footing? One way is by defining a two-dimensional energy space, giving t and b their own axes.
His audio is terrible. What is he saying?
Energy, they are fundamental, such that the potential and kinetic energies are always being converted into one another at equally great but opposite rates. Applying these curves against the same energy axis doesn't actually tell us the whole story, since even though t and b both have units of energy, they are fundamentally different quantities, one related to speed and the other to position.
Okay.
So how could we treat these energies on more equal footing? One way is by defining a two-dimensional energy space, giving t and b their own axes. A single point in this energy space then represents...
Okay, now we're going to plot t against v. in an energy space. Okay.
Sense a particular state of our system. But since we know that energy is conserved, it follows that any such point must lie in a line, along which T plus B equals some constant total energy.
Interesting. So energy is conserved, so there must be an E. T is total, I guess. T plus V is E total. So it's a constant. So this plus this, or this plus this, or right, it should always be a constant. So this length should equal to this length. This is ET and this is ET. So this plus this should equal ET. So any combination of this plus this plus this should always give us a constant. And that is a straight line. Why is that a straight line? I never thought about this. Is this true? This is like 1, let's say this is 10. So this is 9 plus 1 or 8 plus 2. Okay, that makes sense. So this is 10, 9 and 1, 8 and 2, 7 and 3. So that sounds like a linear. That's a linear curve. It's a line. Okay.
ET. Let's represent the given energy state by a vector E. We already know how to express this vector as a function of time. It is simply the kinetic energy function times a unit vector along the t-axis, call it t hat, plus the potential energy function times a unit vector along the v-axis, v hat. Let's write this down in the upper left. We note that this expression relies on two energy coordinates, t and b, to describe the ball's trajectory.
This is a very confusing way of expressing things. So this is a vector, and this is a vector, and this is a vector. So this is some energy. Is this the total energy? I think that this line always represents the total energy. So this vector plus this vector is equal to this vector, which is of a constant magnitude. Okay, t hat is always in this direction, v hat always in this direction. So, very interesting. So we're saying that E, I don't know why he doesn't say ET. Isn't this always ET? Maybe it's not. Because ET is this line and ET is this line. So this is not ET. That's why he needs a vector space to tell us what this is. What is this? Well, we could write just an equation that describes it. I don't know where he's going with this. So the magnitude of t in this direction plus the magnitude of v in this direction is equal to E, whatever that is. So vector E, okay.
For energy space. But this energy trajectory is obviously one-dimensional, since it needs to stay on the line of constant energy. In other words, we should be able to describe it using a single energy coordinate. To do this, we remember from linear algebra that if we can find the constant vector that gets us onto the line, and the vector parallel to the line, we can describe motion along it using a single scalar. Let's use the total energy times v hat to get us onto the line, and define a unit vector L hat along the line, scaled by some number L. The sum of these two vectors then provides an equivalent representation of our E vector. In a way, we could say that we have created a new energy axis along the line of constant energy, with its origin at the tip of the constant vector that got us onto the line. The parameter L then acts as the energy coordinate we seek, since it's effectively telling us where E lies along this new axis. Our next step is to determine...
I didn't follow that. What is he trying to do?
Should be able to describe it using a single energy coordinate. To do this,
a single energy coordinate?
We remember from linear algebra that if we can find the constant vector that gets us onto the line, and the vector parallel to the line, we can describe motion along it using a single scalar. Let's use the total energy times v hat to get us onto the line, and define a unit vector L hat along the line, scaled by some number L.
Okay, so this is a unit vector along the line L hat. Okay. So this is E total times V hat plus L times L hat. That should give us E.
The sum of these two vectors then provides an equivalent representation of our E vector. In a way, we could say that we have created a new energy axis along the line of constant energy, with its origin at the tip of the constant vector that got
So this is a new energy axis.
onto the line. The parameter L then acts as the energy coordinate we seek, since it's effectively telling us where E lies along this new axis. Our next step is to determine L explicitly. We start by setting our new expression for E equal to the first one, and then consider how to express L hat in terms of V.
Okay, so we want to find out what L equals. So E total, I think this is this guy, yeah. E total times V hat plus L times L hat. That's also equal to E, obviously. Okay, let's find out L.
V hat and T hat. Us where E lies along this new axis. Our next step is to determine L explicitly. We start by setting our new expression for E equal to the first one, and then consider how to express L hat in terms of V hat and T hat. Since the slope of the constant
What do we want to find out?
expression for E equal to the first one, and then consider how to express L hat in terms of V hat and T hat. Since the
Okay, so he wants to express L hat in terms of V hat and T hat.
slope of the constant energy line is negative 45 degrees, we can deduce that L hat must contain equal parts,
Oh, it's 45 degrees, okay.
both V hat and T hat, with their signs adjusted to give the correct direction. We then need to add a normalization factor of 1 over the square root of 2 to ensure unit length before inserting into our equation for E. Now, T hat and V hat are of course linearly
What? So 45 degrees, I think this is the cosine of the angle or the sine of the angle. They're both equal at 45 degrees. So he's saying that
both V hat and T hat, with their signs
he's saying T hat minus V hat. So T hat is this direction and minus V hat is this direction. Yeah. That should give you the correct answer, okay?
adjusted to give the correct direction. We then need to add a normalization factor of 1 over the square root of 2 to ensure unit.
Okay, but that's not unit because this is unit and this is unit, but unit plus unit is too big because the hypotenuse, right? It's 1 squared plus 1 squared. That's 2 squared. I'm sorry, that's 2. So a squared plus b squared equals c squared, or a squared plus b squared square root equals c. So we want c to equal 1. So it's a squared plus b squared, which is basically this. Square root he's not explaining this. He's not explaining why he's dividing by the square root of 2. This is 1 squared plus 1 squared. This is 2 squared. Right? One, this is the square root of 1 squared plus 1 squared. The size of this thing is the square root of 2. It's too big. That's right. So he needs to normalize it, make it 1. This needs to be of magnitude 1. It's too big. So you divide by the square root of 2 to make it a unit of unit length. Okay.
Length before inserting into our equation for E. Now, T hat and V hat are of course linearly independent, so we know that the corresponding coefficients on both sides of this equality must be equal.
So let's see this again. So L times L hat, which is unit.
We then need to add a normalization factor of 1.
So L hat is this. So we're multiplying L times L hat, which is this. Okay.
the square root of 2 to ensure unit length before inserting into our equation for E.
Correct.
Now, T hat and V hat are of course linearly independent, so we know that
So now, T hat and V hat are linearly independent. Yeah, they have nothing to do with each other. They're just orthogonal directions.
corresponding coefficients on both sides of this equality must be equal. T
What?
hat and V hat are of course linearly independent, so we know that the corresponding coefficients on both sides of this equality must be equal. Writing this out gives
What?
the square root of 2 to ensure unit length before inserting into our equation.
Let me slow it down 1 second.
And for E. Now, T hat and V hat are of course linearly independent, so we know that the corresponding coefficients on both sides of this equality must be equal.
Corresponding coefficients on both sides of this equality must be equal. What? Now,
T hat and V hat are of course linearly independent.
okay, T hat, V hat, V hat, T hat, V hat are linearly independent.
So we know that the corresponding coefficients on both sides of this equality.
On both, okay, this is both sides of this equality. Okay, they're coefficients, yeah, meaning V and T and ET and L and 1 over, I guess, L over the square root of 2. Okay, they're coefficients, yeah.
Must be equal.
Okay, so, oh, okay. So the coefficient of V hat is V and T hat is T. Now here you have V hat and here you have V hat and here you have T hat. So reorganize this into, like, separate the variables to T hat separately and V hat, and then you'll be able to say that it's V times V hat. Let's see how he does this. You just need to say ET V hat plus L over the square root of 2. Well, you need to multiply this out and then reorganize everything times V hat and everything times T hat. And then you'll be able to say what V is and what T is.
Writing this out gives us two separate equations.
Okay, he doesn't go through the steps, but you end up seeing that V is E total minus L over the square root of 2.
Subtracting the first from the second then gives us a new equation.
T minus V. So T minus V is this minus this. So it's basically this minus this is this plus this. So it's just, right, square root of 2L minus ET, E total. Okay, so that's T minus V.
Equation where we can isolate L.
Okay, finally you can isolate L. So L is equal to T minus V over ET over square root of 2. Where's ET? You need to say T minus V plus ET. Where's plus ET? Okay.
We could of course choose to write either T or
So that's L. That's the magnitude of this vector, okay?
V in terms of the other and the total energy. But in doing so, we would lose information about either the position or the velocity, which seems like a bad idea.
I don't know what he just said. What did he say?
The other and the total. We could of course choose to write either T or V in terms of the other and the total energy.
Okay, you can take T or V and write it in terms of the other, because we have T and V, I guess. I don't know. You can just remove them and just write it in terms of L.
But in doing so, we would
Oh, he said that?
E or V in terms of the other and the total energy. But in doing so, we would lose information about either the position or the velocity, which seems like a bad idea. So we continue to treat T and V as equally important, and thus end up with this expression for L, which is a linear function of the difference T minus V. It turns out that we can actually get rid of the constant term if we first split the green vector into two parts, and then redefine the vector which gets us onto the line, effectively moving the origin of the L-axis to a point halfway across the line. The function that we're now left with thereby
What?
It turns out that we can actually get rid of the constant term if we first split the green vector into two parts, and then redefine the vector.
So he's taking E total over square root of 2. So this is E total over square root of 2 in the direction of L hat. He's saying that's this part. What you're going to have left is L? I don't get it. L is the whole thing, isn't it? L is the whole thing.
If we first split the green vector into two parts, and then redefine the vector which gets us onto the line, effectively moving the origin of the L-axis to a point halfway across the line. The function that we're now left with thereby represents the one-dimensional energy.
Isn't this a different L?
And then redefine the vector which gets us onto the line.
Okay, so this vector is 1/2 ET times V hat plus T hat. Okay, this direction I think is V hat plus, isn't this V minus T or T minus V over the square root of 2 or something? I don't know. Now I'm lost. I don't know what he's doing. He's redefining maybe L. He's saying, okay, let's call this L. After he works so... Oh, yeah, he's redefining L by removing this constant part. He's saying this is the constant. He's removing it. Now he's saying this is the leftover L. This is the leftover L. Okay, and now the question becomes, what is this? What is this? So he's saying it's this. How did you get this? He doesn't show us how he got it. I don't know if it's important.
Green vector into two parts, and then redefine the vector which gets us onto the line, effectively moving the origin of the L-axis to a point halfway across the line.
I don't know. But how did you develop the blue equation? He worked so hard to show every part, but now he's not showing how he got this equation. And I don't even know if it's important. All we know now is this length. But we don't know how he got this. And this is the origin. Why is this? He's saying it's 1/2. Why is it 1/2? It's exactly 1/2. And V plus T, this is the direction. He's saying this is the direction V plus T. It is. Isn't this is V and this is T? Oh, V plus T is exactly this. Okay. And the magnitude is 1/2. This is this exactly V plus T? And the magnitude is exactly 1/2 E total? This is exactly 1/2? So you have this is a triangle. This is a right angle triangle. The hypotenuse is E total. So the size of this is one half E total. So if this is 1/2 and this is 1/2, this is the full size? Probably not. What about this V plus T? V plus T, is it a unit of unit length? I don't think so. This is V plus T. This would not be, V plus T is not unit length. It's too big. You need to divide by the square root of 2. This is probably divided by the square root of 2 squared. So it's 1/2. We need to work out. I don't know why he skipped this step. Okay, so we know this coordinate. This is like a separate coordinate system, I guess.
The function that we're now left with thereby represents the one-dimensional energy trajectory of the ball, as measured along the line of constant energy from a point halfway across it. A nice way to visualize this is by switching to a 3D view, where we define a time axis orthogonal to the energy plane, such that we can actually plot L against the L axis. At t.
Oh my god, this is very unexpected. This is too much. And this is what you need to understand in order to derive the Lagrangian? This is the most confusing derivation I've seen in my entire life. What are we looking at? This is, where is 0, 0? Is this is 0 and this is 0. So this is 0, 0. I think. So this is where the coordinate system starts. So this is V and this is T. But there's also time. So the ball starts here. Time progresses. As time progresses, so what he wants to end up with is a single vector equation L that he's plotting, and that he is that where's the origin of this vector? But I think this is the vector, right? Let's move back a little bit. So this is the vector.
At T0, the system starts out with only kinetic energy, which is gradually converted into.
Okay, so this direction. What is this direction? I'm confused. This is the T direction, and this is the V direction. And this is the L direction.
To the energy plane, such that we can actually plot L against the L axis.
Okay. So, okay, it's really confusing, but so this is, what is it? What is L? What is L? He never explained what we're plotting. What are we plotting? Is it a kinetic? Is it the potential? Is it some? Oh, it's L is just this t minus v over the square root of 2. That's all it is. It's t minus v, whatever that means. What is unique about t minus v? What is unique about L? Why are we plotting L? What information is in L?
At T0, the system starts out with only kinetic energy, which is gradually converted into potential energy as the ball reaches its
So this is not a vector. This is just he's pointing at whatever he's talking about. Because there's no vector in this direction. This is time.
maximum height. And the potential energy is then converted back into kinetic energy as the ball descends.
So, okay.
We can also visualize the symmetry between the potential and kinetic energies if we draw
Where's the symmetry between the kinetic and the potential energy?
the V and T curves on their respective axes and shift our view slightly. Clearly, the curves are essentially mirror images of each other.
I see, okay. The projection of this curve onto the T plane and onto the V plane, they are mirror images of each other. Well, not exactly. It's the same curve. The nice thing is that we're projecting one curve onto two planes. So you're getting some sort of symmetry, which is good. You can visualize the symmetry. That's good.
And the mirror is the L-axis. Another thing worth noting.
So he's saying the L-axis is the mirror. So they're looking at a mirror and they're seeing their mirror image necessarily. So the T looks at L, the mirror, which is L, and it sees V. And the mirror, as we know, it's inside out. So if I'm a guy or a girl, and this is my head, and these are my feet. Who is here? Sheep. What's up, Mr. Sheep? You need to unmute yourself, Mr. Sheep. Can you unmute yourself, Mr. Sheep? Can you do it? La 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 la. Can you unmute yourself, Mr. Sheep? Can you hear me, Mr. Sheep? Well, whenever you figure it out, let me know. Let me see. Unmute. Can't unmute your guest because they chose to mute themselves. So you chose to mute yourself. There's 5 people watching us. That's pretty incredible. Incredible. La 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 la. La 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 la. Let me just. Oh, battery is low. Okay. Let me. Oh, 6 people watching us now. Let me just plug the battery into my iPhone. Let me try and understand where we're at. Okay, so if a person is lying on their side or standing, imagine I'm standing here, the tip is my head, and the two, right, I'm a green guy, this is my left leg, and this is my right leg, and I'm looking at a mirror. L is a mirror. And so this is my head. My head is projected onto the mirror to here, and it's projected onto the V plane onto here. So I am Green Man, and I'm looking at the mirror, and I'm seeing, I don't know what color that is, yellow, and I'm seeing me in yellow. So my left leg is here, and this is my left leg here. Yeah, it makes sense. Okay, so that's good. So now we see the mirror images, right? Before I complained that I can't see the mirror image. Right, in the beginning, he showed us, I don't want to skip here, but this is where we were. And you can see the mirror image. That's when he said, look, there are mirror images, but he didn't prove it. Well, now this is a proof. I mean, it's a whole new. It's one graph that contains all the information. Okay, and we can extract the V curve out of it and the T curve. We can extract all the information back from one curve, the L curve. Okay, I guess.
Is that if we were to choose a different initial height for the ball, or redefine the zero level for the
So he just stretched. What did he stretch? He stretched the V plane. He stretched the V plane. The V plane is the potential energy plane. But 0, 0 is here. I don't know. What's the point of stretching a plane?
potential energy. All it would do is add a constant to the potential energy function, which amounts to shifting the L-axis along the V-axis.
This is V naught. This is energy total plus V naught. Well, if you move the mirror, if you're shifting the mirror, you're just going to shift where the projection is created. We're back to two people. Terrible. Wait, what's going on? Oh, you left? Where's the room? Okay, let me take the room and paste the room. You can join me in Discord if you want. Oh, there's 4 comments. Yo, not right now. Yes, can't unmute right now. Okay. Okay.
It wouldn't change the shape or
So you're saying that V is a function of y, depends on the initial velocity. But this is V as a function of y. I don't think this is V as a function of y. This is V as a function of t. So I don't know.
or form of the L-curve in any way, which is a useful fact to remember. But right now, it almost feels like we're getting a bit lost in energy space. So let's remember our mission here and try to start finding our way back to the equations of motion. But how can this L function help us with this? Well, since it essentially represents the energy equivalent of the spatial trajectory, we should be able to place similar constraints on it. In fact, we should demand that both these trajectories are unique with respect to our given initial conditions. The reason is that if either trajectory was allowed to be distorted, it would mean two possible paths our ball could take between 2 points in space and time, even though we threw it straight up with a given speed, and we'd have no way of predicting which path it would take. This would violate one of the most fundamental assumptions of classical physics, which is that the universe is deterministic. This means that we have a very strong condition to work with. One way to translate it into
This is very interesting what he said. Let's hear it again.
initial trajectory, we should be able to place similar constraints on it. In fact, we should demand that both these trajectories are unique with respect to our given.
So if we have different initial conditions, we should have two separate trajectories. It's impossible to have two different initial conditions and have the same trajectory. So if we start from a different height or with a different initial speed, it should definitely give us a completely different trajectory. Yes.
And initial conditions. The reason is that if either trajectory was allowed to be distorted, it would mean two possible paths our ball could take between 2 points in space and time.
Two paths are both can take, or what? Was allowed to be.
It would mean two possible paths our ball could take between.
Or ball could take. Okay, not bulk, ball.
In 2 points in space and time, even though we threw it straight up with a given speed, and we'd have no way time. The reason is that if either trajectory was allowed to be distorted, it would mean two possible paths.
What do you mean either trajectory was allowed to be distorted? I don't understand.
Our ball could take between 2 points in space and time.
It has to be unique.
Even though we threw it straight up with a given speed, and we'd have no way of predicting which path it would take. This would violate one of the most fundamental assumptions of classical physics, which is that the universe is deterministic.
It's also an assumption of quantum mechanics.
This means that we have a very strong condition to work with. One way to translate it into math is by postulating that no variation of the time average of L is allowed.
No variation of the time average of L is allowed? What is a time average?
We denote this average L bar and use a delta symbol to signify that the variation of L bar has to equal 0.
What is L bar?
We'll consider how to actually define this.
L bar is the average L over time.
Variation in just a bit. For now, we should remember that there is nothing special about the time interval we've been working with so far. This constraint on L bar has to be satisfied for any subsection of the trajectory, no matter how small. And this is what makes it equivalent to saying that the L curve itself cannot be perturbed. We can obtain an explicit expression for L bar by simply
L must be unique. For every initial condition, L must be unique. It's impossible to just play around with L. It can't vary. Whatever L is, it must be unique. There must be a single solution to L. But saying that you're taking the average L and modifying, perturbing it, and the perturbation must be 0, what are you postulating? I'm not following this postulate.
One way to translate it into math is by postulating that no variation of the time average of L is.
Oh, time average. Okay. So taking L, averaging L, I guess that's the line that he's showing over there.
Physics, which is that the universe is deterministic. This means that we have a very strong condition to work with. One way to translate it into math is by postulating that no variation of the time average of L is allowed. We denote this average L bar and use a delta symbol to signify that the variation of L bar has to equal 0.
What are you saying? I don't understand. The variation of L bar is 0. I guess for any initial condition. What does it mean, the variation of L bar? I don't know what it means.
We'll consider how to actually define this variation in just a bit.
Okay.
For now, we should remember that there is nothing special about the time interval we've been working with so far.
Mm-hmm.
This constraint on L bar has to be satisfied for any subsection of the trajectory, no matter.
Okay. Any subsection, you take an L bar. Oh, okay. So any subsection, you take the average L, and you perturb it. So you can't perturb it. The perturbation should be 0. Should not be able to modify it. This is what it means to be a unique solution. Okay.
Or how small. And this is what makes it equivalent to saying that the L curve itself cannot be perturbed.
Right.
We can obtain an explicit expression for L bar by simply integrating L over a time interval, and then dividing by the time interval.
1 second. Let's hear that again. So we're going to subdivide L into infinitesimal subsections, and we're going to make the same claim that for any subsection, delta L bar is 0.
We can obtain an explicit expression for L bar by simply integrating L over
Explicit expression for L bar by simply integrating L
a time interval, and then dividing by the time interval.
That's the average L. Not exactly the average L. This is the integrated L divided by the total time. So it's sort of, that's his definition for average L. Okay.
Our postulate then says that any variation of this quantity needs to vanish. But any such variation inevitably has to come from the integral, which means that we can safely drop the constant factor. For the
I agree.
same reason, we can also define a new L function as simply the difference t minus v, which we will use throughout the rest of our calculation.
Because you're just making a claim. Yeah, the postulate has nothing to do with the constants, so you're just removing the constants. Okay.
Calculations. This new function is how the classical Lagrangian is usually defined.
So that's the definition. That's the squiggly L. That's the Lagrangian. Okay.
In most treatments of Lagrangian mechanics, students are simply handed this formula and left wondering why on earth one would take an interest in the difference between the kinetic and potential energy.
I love this claim that everyone else just throws it at you and says, well, that's the way it is. And he actually went through a lot of trouble to derive the Lagrangian
energies. We have now seen that, apart from a constant factor, the Lagrangian can be thought of as a trajectory through energy space.
Very good. It's a trajectory through energy space,
which in turn represents a trajectory through regular space. With that said, let's continue, replacing L by the Lagrangian. The integral that we're left with is commonly denoted by S and referred to as the action, which has units of energy.
So the integral is called S, and it's called the action, referred to as the action. Energy, units of energy. Okay.
G times time.
Oh, energy times time. Okay.
The action is directly proportional to the signed area between the L curve and the time axis.
To the signed area between the L curve and the time axis. But what you're showing is, I don't know what you're showing. What is the purple? This sign, I don't understand.
This means that time periods during which the ball was moving quickly, such that it had more kinetic energy than potential energy, contribute positively to the action. On the other hand, time periods during which the ball had less kinetic energy contribute negatively. The term action therefore seems to make good intuitive sense.
Is it supposed to be balanced? Doesn't look like it's balanced. What's defining this cutoff? The cutoff is that's the halfway. That's the 45-degree angle that we took, isn't it? So this integral.
Moving on, our postulate can now also be restated in terms of the action. This new form is known as the principle of stationary action. But of course, it still carries the same implication, that we allow no distortion of the actual trajectory.
Okay, that's what we're saying. That's what we're saying. We're saying that we don't allow a distortion in the actual action. So basically, what we're saying is it's unique. Whatever the answer is, it's deterministic. We're saying it cannot be modified. You cannot touch it. It's holy of holies.
This might have been a lot to take in, so let's make a quick recap of the essentials of what we've done so far before we continue. We started out by determining the equations of motion for a ball using Newton's force laws. We then wanted to find a way of arriving at this result using the concept of energy. For this purpose, we entered energy space, where we were able to write down the classical Lagrangian, which we interpreted as a one-dimensional representation of the ball's energy trajectory. We then argued that the spatial trajectory of the ball must be unique with respect to our initial conditions, which implies that the Lagrangian must also be unique.
Wait, what?
As a one-dimensional representation of the ball's energy.
Yes, it's one-dimensional. Yeah, it's good.
Trajectory. We then.
It's just L space, Lagrangian space. It's good.
Argued that the spatial trajectory of the ball must be unique with respect to our initial conditions.
Must be unique. That's the perturbation. Must be zero.
Which implies that the Lagrangian must also be unique. And we have now formulated this mathematically in the principle of stationary action.
What is the purple? I didn't get the purple. Unless you, I mean, why is the purple, what is this half, what's defining this halfway? Like some of it is over this line, some of it is under the line. Oh, it's T minus V. But that is L space. Isn't it just... Why is it... Why is that the area? So the Lagrangian... Because it's not... I mean, this is L. This is not the Lagrangian. So the integral of the Lagrangian... And this is L. This is the integral of L, or is this the integral of the Lagrangian? I guess the integral of L is the area under this curve, is this entire area. And if this is the integral of the Lagrangian, then it's the square root of L. Why is this area the square root of L? I don't know. He didn't explain it.
Okay, so that's where we stand. Let's now try to work with this postulate, which tells us to consider variations of the action. It turns out that it is beneficial to do this somewhat indirectly, by instead introducing a variation of the spatial trajectory. So let's return to regular space, and while we're at it, let's add some initial height to y. It will help make this section a bit more clear. Now, in order to vary this trajectory, we introduce a function of time eta, which is 0 at t0 and t1, such that we can add it to y without disturbing the start and end points. We also introduce a parameter epsilon, which is just a number we can tweak in order to alter this new trajectory. Let's call this altered trajectory y star, and note that we can always get back the true trajectory by bringing epsilon to 0. The term epsilon times eta thus represents a variation of the spatial trajectory, which in turn induces variations of the Lagrangian and the action. To see this better, let's label the perturbed action with a star and plot it as a function of epsilon. The true value of the action is represented by the point on this curve where epsilon equals 0. Decreasing or increasing epsilon then represents moving away from this point, effectively introducing a variation.
My God, this is so confusing. So this is the perturbed action. This is delta S. What is delta? I mean, the equation delta S, this is, it's epsilon eta of t, I guess. Did we define eta of t? I don't know.
We also make another key observation.
This is S star. This is the perturbed S. This is unperturbed. I guess this is the original, and this is the perturbed. The original, and if you perturb it, you get to here. How does he know this is what it looks like? I mean, who said, what is this shape? You didn't tell us. I mean, you defined eta to be an upside down parabola. This is a right side up parabola. I don't know.
Which is that in the case of the thrown ball, the action we expect to observe appears to be a minimum of the perturbed version, such that its derivative is 0 at this point.
The derivative with respect to the epsilon from epsilon equals 0. What does this mean? Plug in epsilon, or as epsilon tends to 0? What are you saying? I don't know what he's saying here.
This is no coincidence. It turns out that the principle of stationary action ensures that the observed action is some kind of extremum, be it a maximum, a minimum, or
But you're showing here it's a minimum. So what do you mean it could be anything?
an inflection point. Most commonly, it seems to be a minimum, which is
What do you mean most commonly?
why the principle of stationary action is often referred to as the principle of least action. The reason why the action we observe happens to be an extremum of something more general is pretty much unknown. In the more
Wow, pretty much unknown. So you're making a claim about this universe that if you perturb the trajectory, you're increasing you're increasing the action, and you don't know why.
precise theory of quantum mechanics, the stationary action represents only the most probable trajectory, and extremely
Wait, what? What do you mean quantum? What about classical?
unknown. In the more precise theory of quantum mechanics, the stationary action represents only the most probable trajectory, and extremely small deviations are then actually possible. To me, this seems to hint that the extremum corresponds to some kind of stability point for our universe, which allows us to classically determine trajectories with extremely good accuracy.
I don't understand. You just finished developing this method and you're claiming you don't know why it's true? Why this method gives you correct results? You don't have proof?
But this is basically metaphysics, so take it with a grain of salt.
What do you mean metaphysics? What? I'm so lost.
The important thing
This is the best, by far, Lagrangian development that I've seen anywhere.
is that we have now managed to translate our postulate into a form we can actually work with. So let's now go ahead and do just that, by computing the derivative of S star with respect to epsilon. The derivative operator can here safely be moved inside the integral.
What is this? So ds star d epsilon is d epsilon of the integral from t0, t0 to t1 of the Lagrangian star. This is the perturbed Lagrangian, which is a function of y star, which is the perturbed trajectory, y dot star, the perturbed velocity, dt. I mean, this is just taking S and developing S star and then taking the derivative with respect to epsilon. He never said that the Lagrangian is a function of y and y dot. This is the first time he's mentioning it. I wish I could have a bigger screen to see the details. I don't want to have to skip. We're now at 1903. Just remember 1903. So S is a function of the Lagrangian. The Lagrangian was never, he never said that anything about the Lagrangian that it's a function of y and y dot. I don't know why people do this. They just say, oh, it's a function of y and y dot. Why? Why do you say that? Where does that come from? I'm scrolling through, but it's hopeless. Okay, we were at 1902.
Moved inside the integral, where it is applied directly to L star.
What?
Into a form we can actually work with. So let's now go ahead and do just that, by computing the derivative of S star with respect to epsilon. The derivative operator can here safely be moved inside the integral, where it is
Okay, so the derivative with respect to epsilon, so he says, well, this is an integral over dt, so you can move the derivative into the integral because the Lagrangian has nothing to do, well, the integral has nothing to do with epsilon, I guess. I don't know.
apply direct.
Right, this is the area under the curve of the Lagrangian star, the perturbed Lagrangian. So it's just the area under the curve of the perturbed Lagrangian. So it's the area under the curve of the perturbed Lagrangian. And this is the perturbation. So this is for a given perturbation. I don't know. I honestly don't know.
Directly to L star.
Okay, so it's d perturbed Lagrangian over d epsilon. Okay.
We then proceed to expand this derivative using the chain rule.
Okay, so what is the Lagrangian? The Lagrangian is, well, it's a function of y and a function of y dot. So this is dl dy dy d epsilon plus well, it's a function of y and y dot. That's the claim. The Lagrangian is a function of y and y dot for some reason. Unexplained. Is this the chain rule? So once we're taking the derivative with respect to y and once with respect to y dot and then y dot d epsilon. It's two partial derivatives. It's the partial derivative rule, partial derivative chain rule. Is this the chain rule? This is the chain rule. And this is the total derivative. You see there's a partial and a total derivative. Is this the total? I think this is the total derivative. So we're taking the total derivative. The way to take a total derivative over epsilon is the partial with respect to y and then y with respect to epsilon, but y star is not partial with respect to epsilon. There's nothing partial about it. So that's why the notation is total. Okay. This is skipping so many steps. Oh my god.
From the definition of y star, we can now work out its derivative with respect to epsilon, which is simply eta. Also, if we take the time,
so y star or dy star d epsilon, if you take derivative with respect to epsilon, is just eta of t. Okay.
derivative of y star, and then differentiate the result.
Okay, y dot star is y dot plus epsilon eta dot. Because eta is a function of t. Okay. So this is y dot star. So the epsilon is just eta dot.
With respect to epsilon, we get back the time derivative of eta.
Okay. So the partial Lagrange dy eta and partial with y dot eta dot. Okay.
Let's now take a closer look at the second term of the integrand. When we see a product of functions, we can often rewrite it using the product rule for derivatives. And after a bit of trial and error, we can arrive at the following result, and then solve for the term we want to replace.
So partial dl dy dot eta, he's taking the derivative with respect to time. Why? You're integrating. Why are you taking the derivative? Because this is eta dt. This is eta dt. He's taking dt out. That's allowed. Because the Lagrange star dy dot star is not a function of time. That's the claim. Jesus Christ. What do you mean trial and error? dt. This is the most confusing. He's skipping way too much for this to be productive. And this is, I've never seen anyone going into this all this detail. Everyone skips every step imaginable. The partial Lagrangian partial of y. Oh. But what is this? What is this? Where is he going? Oh, because he wants to integrate. So he's integrating by trial and error. He's showing us how he's going to integrate it. Okay, by finding the derivative. He's saying if we take the derivative of this, we get this. Therefore, this is the integrand, or this is the integral. This must be the integral of this because, right, if you derive this, you get this, I think. Do you? I mean, no, I don't think that that's what he's doing. So he's taking the derivative. He's doing by trial and error. He's going to show that he's going to end up with this partial dl over dy dot times eta dot. I don't know what he's replacing with what. Where's eta dot? The only eta dot is here. What? I don't know. I need to see the end.
We proceed to insert this back into our equation, and we then split the result.
So that is what he found. Okay, let me see. Okay, here it is. So there is eta dot. Okay, this is this. And it's equal to this derivative of t. So if you take this, the internal is the integral. Okay, but what about the first term? I guess you can leave it there. Okay. Now, let's just, how did he arrive at all of this? So he said, if you just take this, you take this, okay. So you expand it, it's this times this plus this times this. This is the chain rule, right? I think this is the chain rule. It's probably, is it the chain rule? Chain rule of derivatives, is it? Okay, so it's the derivative of the first part times eta plus this, the first part times the derivative of eta. Okay. So now this is what we want. So this is equal to this minus that. So dl dy dot eta minus dl dy dot eta. Okay. So now he's replacing it. Okay.
We proceed to insert this back into our equation, and we
Okay.
then split the result into two integrals.
Okay, so it's two integrals. So this is dl dy. This is dl dy dot eta. That's this thing. So this thing is one integral, and this is dl dy eta minus this thing, dl dy dot eta. Okay. So it's two integrals, okay?
To evaluate the first one, we just note that integration and differentiation are essentially inverse operations.
Let me see, d dt. Okay, so all we're left with is dl dy dot eta.
So the primitive function that we need to evaluate at the limits is just the part inside the time derivative.
Yes.
But remember, we required eta to be 0 at both t0 and t1. So this entire
So okay, yeah, that is true. I don't know why we have this demand of eta, but fine, it's fine. Okay, so it's 0 minus 0, so this goes away.
term simply vanishes. And we're left with the second integral, where we can factor the integrand.
We can factor. So if eta is outside, this is dl dy and dl dy dot. Okay.
At this point, we come back to our updated postulate, which says that this remaining integral must vanish when epsilon equals 0.
Okay.
Which means that we get back the actual trajectories.
What just
The
happened?
last key realization we get back.
So we just lose all the stars. At epsilon equals 0, we lose all the stars.
The actual trajectories. The last key realization to make is that we never actually defined what eta looks like, besides the fact that it is 0.
What eta looks like. Wait, what?
The last key realization to make is that we never actually defined what eta looks like, besides the fact that it is 0 at t0 and t1. This essentially means that the integral needs to vanish for any such eta, which is possible if and only if this other factor of the integrand is 0. We thereby finally arrive at this very important result, which is known as the Euler-Lagrange equation for the coordinate y. Actually defined what eta looks like, besides the fact that it is 0 at t0 and t1.
Okay, so when we integrate this thing, then okay.
This essentially means that the integral needs to vanish for any such eta, which is
So when we end up plugging in T1 and T0 for eta, but eta is a function.
possible if and only if this other factor of the integrand is 0.
This is 0? What do you mean it's 0? I mean, it's some curve. Why would it be 0?
We thereby finally arrive at this very important result, which is known as the Euler-Lagrange equation for the coordinate y. It seems reasonable that if we were to insert a Lagrangian for the ball system into this equation, we should get back something useful. So let's go ahead and try it. We see that the partial derivative of the Lagrangian with respect to y is negative mg, and the partial with respect to y dot is m times y dot. If we then carry out the time differentiation, we end up with this familiar expression, which is the exact same equation we got from Newton's force law, and it will then obviously give us back the same equations of motion.
Jesus Christ, oh my God. I've never seen such a complicated derivation.
The difference is that we now didn't have to consider any forces, only energies. This may not seem like a huge deal in the case of this very simple system, but the usefulness of Lagrangian mechanics becomes much more apparent when we consider systems consisting of several moving parts and having several degrees of freedom. The general idea is that we can then apply the Euler-Lagrange equation once for each spatial coordinate. It also turns out that Lagrangian mechanics allows us to conveniently obtain equations of motion in terms of generalized coordinates, which do not necessarily have to be Cartesian. But more on this in the next video, where we'll consider how all this works out in practice.
Oh my God. When was this? 2 years ago. My God, what does she say? Introduction to Lagrangian?
Hi, my name's Bryony. I'm a condensed matter physicist. I completed my degree under the supervision of Professor Michelle Simmons, who won 2018 Australian of the Year. So in this topic, we're looking beyond the basics at Lagrangians and Hamiltonians. So I'm going to start off by introducing you to this idea called the Lagrangian. But even before we get into that, I want to step back and think about what do we mean when we talk about describing a system. So if we have a system, be it a pendulum, a car rolling along a track, anything, the way we describe it is by its position, its velocity, and its acceleration. And all of those things normally we find through the equations of motion. So have a look at this system here. This is a cart, so a large mass on this track. We're going to assume it slides without friction. And underneath it, we can see there is a string with a mass tied at the end. So we can see that if I bring this back here and I then push it forward, you can see that as this string moves, that it affects the motion of the cart. As the cart moves, it affects how the mass of the end moves. So a system like this is pretty complex. If I asked you to derive for me the position, velocity, acceleration as a function of time for this, could you do it? Because if you could, please let me know, because I haven't even bothered trying, because it would be a horrendous problem. So instead, we need to have a different way, a nice and prettier way. So in the 18th century, a dude called Pierre-Louis Maupertuis came up with this idea that is any physical system will follow a path of least length. Basically, Mother Nature is lazy and does as little work as possible. So it actually turns out that you can generalize this not just physical systems traveling along a path. You can actually generalize it to anything. It's principle of least action, which is that kind of any system undergoing some change, whatever, it will behave in such a way that the action is minimized. So we can define action this fancy way. With S is the integral from T1 to T2, where T1 is like our initial time, T2 is the final time, so that would be T1, and then maybe T2 as it's moving. L is our Lagrangian, which I'll be discussing later, and dt is obviously time. So this equation looks scary, but it's actually really beautiful and combines a lot of really cool things in physics. So don't be scared of it, and even more don't be scared of it, because we're now going to put it away and just look at this L. So this L is this magic Lagrangian. The thing that I've been promising will explain this a lot nicer than our ugly Newtonian mechanics can. So our Lagrangian actually is not defined using our normal position, acceleration, velocity naturally. You can start with a function and then do some cool tricks to it to turn it into a Lagrangian. And if you've done any engineering or economics, you've probably played around with that. But the nicest way...
Yeah, in economics, that's how they teach. That's basically what we do. We use Lagrangians. But I never understood why.
That we do it in physics, at least, is by the energy. So when Maupertuis first defined his principle...
It wasn't Mr. Lagrange?
He used this quantity T and said this quantity T is minimized, blah, blah, blah. But it turns out this quantity T is actually our kinetic energy. So we can then define our kinetic energy. Instead of using K, we use T, because we like to be special sometimes. We also need to involve our potential energy. Potential energy, in this case, we'll take as V. So we can define our Lagrangian quite simply as L equals T
Quite simply. Just take it.
minus V, where T is our kinetic energy and V is our potential energy. So before we get started into actually finding the Lagrangians, I'm just going to give you a little note on some notation. So we remember from earlier in this course that we can express the velocity and the acceleration as derivatives of the position. So we know that velocity is ds.
Okay, I don't know what to do anymore. This is very, very difficult. This is just murderously difficult. No one is explaining it like a normal human. No, I'm not sharing the right tab. Wow. Good to know.
Is any semblance of free market, of market economics, of freedom, of not even capitalism, just a little bit of freedom in the economic realm, that is dead. There's nobody standing for that. Nobody that actually advocates for economic liberty anymore on the American political scene. And that is definitely true of these two. So the one thing is, you'll see a competition between the two of them to give away as many goodies as possible, and to pretend that there are no economic problems. There's no debt problem, that we're spending government money left and right, both of them. There are no issues, and there's certainly no market solutions to anything. All right, let's see a few more quick stories. All right. Yeah. Okay. Google. Yesterday was the first day of the new Google antitrust lawsuit. You know that Google lost the first lawsuit, the lawsuit that claimed that it was a search monopoly. It is lost, and now we're waiting for the judge to decide on a remedy, and of course, waiting probably for an appeal by Google. We'll see how that plays out. but they lost their first account. They are now declared monopoly on search, and there are a bunch of remedies that the court is looking at, including breaking Google up. Well, yesterday, another lawsuit started, and this is a lawsuit claiming that Google holds a monopoly over advertising, over online advertising. It certainly has a large market share of a particular sliver of online marketing, online advertising. If it loses this one, which I think is very likely, then it's going to be hard to imagine how Google survives. Now, I know a lot of people hate Google for a variety of different reasons, and there are lots of reasons to dislike Google, given the political correctness, given the stupidity of the AI that they launched, and given that sometimes the search results are just not helpful. And clearly, when it comes to politics, many of the search results are biased. The reality is that Google is a great company. This is a company that was built by a couple of Stanford students, basically in the garage, not exactly, but basically in the garage, in the late 1990s. It was one of many search engines, one of many companies competing to provide search functionality. It clearly won that battle to the point where it dominated, not because it had some special market power, not because it could bring to bear, any massive amount of money or anything like that. It won because it provided a better product, a better service. Its search engine was just more effective and better. And if you don't believe me, just try running a search on Bing and compare it to search on Google. And Google is just, from all the searches I've done, always been better. This is a company that figured out how to monetize search with advertising, invested heavily in the technology of advertising, in efficient advertising, and has done phenomenally well in that. They've never stopped improving their search, invested heavily in AI, invested in a lot of different things, including self-driving cars. We'll get to self-driving cars in a minute, and other technologies that will all benefit from ultimately. It was, from all indications, it was a fun company to work for. It might be a company already in decline in the sense that it's going to face competition primarily from AI, which means both its search is unsafe and its advertising model is unsafe, because AI will replace it all. I use Chrome browser, which is a product. And yet the government is going to step in and decree the company that provides all of us with a product for free is a monopoly, should be destroyed, should be changed, not on the basis of the marketplace, not on the basis of individual decisions in the marketplace, but on the basis of bureaucratic fiat, on the basis of authoritarian dictate, on the basis of a fascist where some elites, some central planners dictate which mergers can go through, which can't. Nippon US Steel can't do that one. And again, this is like Nippon Steel. This is a bipartisan issue. The first lawsuit against Google was brought by the Trump Justice Department. So Trump was responsible for the first lawsuit. This lawsuit is all on Biden, but it doesn't matter. It's not like Trump or Republicans disagree with this lawsuit. They support it 100%. Today, there is, I've said this many times, I'll say it many, many, many times, unfortunately, there is no political party today that stands for even a semblance, even an iota of freedom in the marketplace. They're both statists, they're both interventionists, they're both central planners. They want to dictate our lives and run our economy for us. We know how that ends. That does not end well. But, this Google antitrust court case is going to be interesting to keep track of, to watch and to see how it lands up. All right, Telegram. So we all know about the founder of Telegram being arrested in France. We talked about this, accused of the fact that the platform was being used by bad guys, and that Telegram did refuse to basically respond to police inquiries, to law enforcement inquiries about illegal transactions, illegal things being communicated, and illegal child pornography being exchanged on the platform. As we know, the founder of Telegram, who was arrested, is being released in France on bail, is waiting a trial. In the meantime, it turns out that Telegram is changing its policies, its moderation policy. It's actually going out there and improving the transparency of the platform, improving moderation of the platform. So, for example, they're going to implement a bunch of changes over the next year. Some of those changes appear already being taken. For example, the company FAQ page has changed just in the last couple of days. One section, for example, that was titled, "There's illegal content on Telegram. How do I take it down?" Initially, Telegram response to the question read, quote, "All Telegram chats and group chats are private amongst their participants. We do not process any requests related to them." That has already changed. So now the verbiage on is all Telegram apps have report buttons that let you flag illegal content for our moderators in just a few taps, and then they give you the instructions on how to fill out the report and go there. So Telegram's changing its moderating practices. It's going to be much easier to report illegal stuff. They are going to be much more friendly to law enforcement. I think mostly this is good. Mostly this is about crime. Mostly this is about really objectively bad stuff. I don't think that the Telegram case was ever really about free speech. It was about whether you can use this platform to engage in illegal activities without being caught. And I think that some of that at least looks like Telegram is going to block. Now, we'll see whether that sticks, whether that's sustainable, how long it lasts. We'll see exactly what happens. The issues with Telegram are progressing. All right, let's see. What do we want to do here? Okay, two last stories. Starlink and Waymo. Starlink. Starlink has now, basically Starlink now controls 2/3 of all satellites in the sky. 2/3, 66% of all satellites in the global sky are controlled by Elon Musk. People are flipping out over this. Brazilians, who of course are banned Twitter in Brazil, they are concerned that one person could make the decision to take down service for hundreds of thousands of people. I wonder if they're concerned about a Brazilian judge who can take down service for tens of millions of people. But yeah, they're talking about Starlink, so they're worried about Starlink. Bureaucrats all over the world supposedly are now worried about, hey, Elon has a monopoly over space satellites. Over space satellites that provide internet. Now, of course, there's terrestrial competition. But this is kind of big thing. It's kind of spooky. And it's a little out of their control. Although the Brazilians did force Starlink to cut subscribers from X, to ban X on the platform. So they should have some control over it. But this is great. You got to love this. And again, I have a love-hate relationship with Musk, obviously. Half the time he does great things, half the time he does bad things. But, it's exciting to see how successful this venture has been. I don't know if it makes any money, but it's been an incredibly successful venture. There are thousands of satellites now up, Starlink satellites up in the sky. Again, 2/3 of all the satellites Elon Musk owns. That's amazing. Well, not Elon Musk, SpaceX. That's amazing and inspiring and scary to the bad guys, scary to the bureaucrats, scary to people who want to have control of our lives, and suddenly they don't have the control. Elon Musk has control. Let's look at that. They're unhappy about that. All right. Finally, yesterday we talked about driverless trucks, right? We talked about the driverless trucks in Texas. And today, the same website, this is Understanding AI, which is a Substack, has a report on driverless taxis and how they are doing. This is, if you remember, Waymo was running an experiment primarily in San Francisco. It turns out they also been running an experiment in Phoenix. So both in Phoenix and San Francisco, you can get into a driverless taxi. No human being running the taxi. We now have some data. We now have some data about the safety of these driverless taxis. So here's some information. Since Waymo started in San Francisco, Phoenix, it has had 20 crashes with injuries. Right? That's through June, so it's not up to date today, but it's through June. 20 crashes with injuries. That sounds like a lot. 20. But when you take into account that Waymo driverless cars have traveled more than 22 million miles, it's not a lot. Not a lot. Waymo taxis have been involved in fewer than one injury-causing crash for every million miles of driving. Now that is much, much better than typical human driver. We'll get to those stats in a minute, but even those crashes, even the 20 crashes with injuries, many of them were not caused by Waymo, even though they have to report it. So, for example, I'll give you an example. On Friday evening, last November, police chased a silver sedan across San Francisco Bay Bridge. I'm reading from the bottom. The fleeing vehicle entered San Francisco and went careening through the city's crowded streets. At the intersection of 11th and Folsom, it sideswiped the front of two other vehicles, veered into the sidewalk, hit two pedestrians. Right. So this car, driven by a human being, running away from the police, hit two pedestrians. It appears that both pedestrians were taken to the hospital. One of them suffered major injuries. The driver of the silver sedan was injured, as was a passenger in one of the other vehicles. So 4 people overall were injured. Now, the third car that was hit was a Waymo robotaxi. Nobody in that car was injured, and yet Waymo was required to report the crash to the government agencies, to the database. So one of the 20 crashes, for example, that its cars were involved in was a crash that it had no way of evading. Some speeding, careening, crazy guy crashed into a Waymo car, caused injuries, but those injuries are counted against Waymo. So even the 20 is an exaggeration. But here's some of the stats, based on, given that we know that. Waymo estimates, this is again according to the article, Waymo estimates that typical drivers in San Francisco and Phoenix would have caused 64 crashes over those 22 million miles. So Waymo vehicles get into injury-causing crashes less than 1/3 as often per mile as human-driven vehicles. And this is by the most general definition of injury-causing accident possible. Now, if you look at crashes that trigger an airbag, so not injury necessarily, trigger an airbag, driverless Waymo cars have experienced just 5 crashes where an airbag was deployed. Typical human driver in Phoenix and San Francisco would have experienced 31 crashes over 22 million miles. Waymo is 1/6 as likely as human drivers to experience this type of crash. Waymo is expanding dramatically. About a year ago, Waymo provided 10,000 rides per week. Right now, last month, it was providing 100,000 rides per week. And growth is going to be dramatic over the next period. Again, even if you look at the crashes that Waymo was involved in, 16 involved a human driver rear-ending a Waymo car. And I think pretty much everybody recognizes that whoever hits you in the back, they're responsible. So, and yet Waymo had to report those crashes. So you take the 20 and you subtract 16, that's already 4, and then you had this car that careened into a Waymo car that had nothing to do with Waymo, there's another one that's only 3. You can see that if you start really looking at these crashes, maybe there weren't any. Indeed, 3 of the crashes was a human-driven car running a red light, crashing into a Waymo, and it couldn't get out of the way fast enough. It could very well be that the number for Waymo is 0. 0. Now that's unbelievable, and it's a real revolution. And if all cars are driverless cars, and they are communicating with one another, or even if they're not driverless cars, the cars start communicating with one another so that they can anticipate where another car is going to be. You can imagine this becoming not only safer, but faster, more efficient, more productive. It changes the way we move around completely. I mean, I'm not sure that in the future we will own cars. It might very well be that we will be hailing driverless vehicles to pick us up and take us to a place. We don't have to own the driverless vehicle if there are enough of them on the road. We don't have to have garages. We don't have to maintain cars. Those will all be maintained by the people who own the driving service. Having a chauffeur, basically. I mean, if regulators allow this, and if not in my backyard types allow this to happen, we could be on a real revolution in transportation, which would change a lot of people's lives. Imagine those commutes, those long, traffic, intense commutes. Okay. Imagine dealing with them in a driverless car. You'll be a lot more efficient because driverless cars, again, can be a lot more efficient. They don't, for example, slow down to look at the accident on the other side of the highway that has no relevance to your own life. I mean, the number of times you get stuck in a traffic jam, and you can be stuck in a traffic jam for an hour, and then you finally get to the source of it, and the source of it is an accident on the other side of the highway, and it was all caused by the fact that a few drivers slowed down to look, and that created this cascading effect. Driverless cars don't slow down to take a look. So we could be on the real verge of a revolution when it comes to transportation. I think is super exciting. All right, we can end there. Keep that story for tomorrow, and we'll move your super chats to center stage here. All right, so guys, you need to ask more questions. And those of you who are watching live, please consider supporting the show, doing super chats, or doing stickers. Let me thank the sticker people. There's some people who gave stickers. Mary Aline, thank you. You started us off. And thank you, Stephen Hopper. Thanks, guys. Really, really appreciate the stickers. All of you could be doing stickers, value for value. You're obviously listening. You get something out of the show. Please consider repaying that value with a small contribution on a sticker. $50, $50, $100. I also remind you that those of you who are not listening live can support the show to a monthly contribution. You can also, by the way, on YouTube, do an applause. And that'll allow you to do a sticker in a sense in YouTube. But even better is a monthly contribution on PayPal through youngbookshow.com/membership or on Patreon, just put Young Book Show on Patreon. And supporting the show that way monthly is a massive value to me, the show, to its future, to making this kind of a permanent part of American culture, right? Your culture. I don't know about American, it's your culture. And if you're interested in sponsoring a show, if you want to take a topic and have me cover it, it's $1,000 to sponsor the show. We can do that. There's Iron Institute to sponsor the show. This conference Iron Institute is holding in, we need to do one in Australia. It's Ironman.org. Pay you to go to the conference. Any place in Asia, and they get you into the conference for free. And teams in Taiwan. So, speaker, fun guy, he'll be there. You should all come /start here. Fight Life, PHI, nutrition, things like that. The integrated us are kind of flooded with be fun. The number one, this will, and you can get it. And his view for the sticker, really appreciate. Behind on the super chat. So I know I missed some yesterday, and I'm gonna thin. So please consider also interesting tourist recommendations in California. I don't, not something the museum in San Francisco. There's really good text. I'm trying to think of. You could drive by the Twitter building in San Francisco, but I'm not sure you get much out of it. A lot to add. It's in the park. It's in. And says there's a computer history museum. Computer history museum in San Francisco. That would be. Yeah, I think I've been there. The Palace of Fine Arts. Thank you. Ian. Palace of Fine Arts, again, it has some of the best views in the world. The museum in the park is the Young. Right? The Young Museum. The Young Museum. Anyway, it's in Golden State Park Art Museum. And Golden State Park has a number of museums with a bunch of local objectivists. Okay. What about a magazine like Playboy that did interviews with an extremely wide range of people and views? They interviewed Nazis, communists, Ayn Rand, Southern racists, abstract artists, politicians of many stripes. God, I didn't know Playboy did interviews with Nazis. I find that bizarre. I find it bizarre they did them, and I find it bizarre that people tolerated it. So I don't know firsthand that Playboy actually did interviews with Nazis. Communists, for a variety of reasons, are just more accepted in the culture. I think that's sad about the culture, but they are. But for Playboy to do an interview with a Nazi, it's serious. Yeah, yes, I would say that it would disqualify that magazine. It would take it. I would cancel my subscription immediately. So I think Nazis and so many real communists.
He had a Playboy subscription.
Real communists, but people who apologize for Stalin and Pol Pot, and this is why I won't speak with Chomsky because he's an apologist for Pol Pot. People like that, I don't see how you can tolerate. Right. So, yeah, I'd be curious if there's really an interview with a Nazi Playboy. Or he says, according to Pew, the percent of Americans who identify as Christians has. Let me say one other thing. One second. Let me stop there. Let me say one other thing. Here's another difference between Tucker interviewing a Nazi and with no pushback, or a Nazi apologist, and Playboy. Playboy interviews a Nazi. Nobody thinks, well, Playboy's Nazi. It's clear that Playboy's interviewing for whatever reason. It's not clear to me why they would interview him, but for whatever reason they're interviewing. But it's not a reflection on them in terms of their views. Tucker interviewing a Nazi apologist is absolutely a reflection of his views, because we know his views are very close to that already, if they're not there yet. We know he has a history with these kind of ideas and dabbling in them. So him interviewing an Nazi apologist makes it seem like, yeah, he's one too. He's one too. So I do think it's more problematic for somebody like Tucker to do it. And it's incumbent therefore on somebody like Tucker to push back against, if he is doing the interview, to push back against the person in order to clarify that he doesn't agree with them. But in this case, it's not clear that he doesn't agree with them. And it's not clear that he wants to take a stand. He likes ambiguity. He thrives on the ambiguity. There's no ambiguity with about Playboy. Playboy was not. Right? So there's a bunch of confusion about the museum in San Francisco. There's the Legion of Honor Museum, there's the Palace of Fine Arts, and there's the Young Museum. And I don't know which is which. So look them up online. But there's a great museum at the edge of Golden Gate Park with a magnificent view that has fantastic sculptures and paintings. And I think that's the Legion of Honor. I think that's what it is. Going back to Owie. According to Pew, the percentage of Americans who identify as Christian has dramatically fallen in the 21st century, while percent of atheists has risen. Do you think Christianity is getting politically influenced despite declining culturally?
Okay. Yeah, I don't know if I'm going to publish this video. It's too difficult. Okay, let's end here.